live now. And let me, Christian is
hey,
also. Hi, Christian.
Hey, Rajan. Hi, Christopher. Nice to see you.
Good timing. We just started. Just like literally went live there now. So.
Yeah, I followed you a couple of minutes, but you didn't recognize I was backstage. So.
Oh, all right, cool. Okay, so no, I didn't, because I was sort of I don't know, what did you catch there? I was sort of online trying to read Rajan's comments. So, oh yeah, so this is what we're going to go into now, is modified Maxwell equations.
Yeah.
So this is a paper that you wrote, is it, Rajan, in about 2018, I think?
Yeah, it was like 5 years ago, almost.
Okay, and if you read my paper, you read that attempt I made at quantum gravity, yeah?
Yeah. So you got a lot of things in there. You are trying to import the standard model, the all the things that is into our fold. That's a great attempt, Christopher. Fantastic.
Yeah.
So
thank you.
Yeah. So, because we need that. We need that because people are going to refer to that. No matter what we do, we have to go back to the what is available now, and then we have to kind of merge, kind of see how they fit together.
Well, this
our
is it.
model.
I mean, there's an interesting aspect to all this. So I know for the last number of years you've been talking about superluminous, like three phases of matter, three realms, whatever, and then the superluminal realm, and then you've had this idea of monopoles, magnetic monopoles that are superluminal for a long time.
Yeah.
Yeah. So I just noticed that so my new kind of quantum, I don't even know if you could actually call it a quantum theory of gravity, but whatever it is anyway, has magnetic monopoles in it, and it also has a superluminal element. So, and it's in a higher dimension as well. So I thought that's interesting from your research, your perspective. I think maybe, yeah, you could look into that and develop that maybe.
Yeah, I like the idea of Lagrangian because, but then we have to bring that Lagrangian back to our type of thing. Like you did a data modeling with a Fourier Lagrangian. So there are like pieces of puzzle,
Cool. Okay, well, so my what I did was I got ChatGPT to sort of help me formulate. Well, I formulated it myself, and then I asked ChatGPT to do it, and pretty much gave me the same answer. So I was like, now that doesn't mean it's right, because I don't know much about Maxwell's equations, and ChatGPT is ChatGPT. So what I got anyway was the grad of well, there's cross and then there's dot product. So the dot product of the electric field equals the charge density divided by the, what is that, the permittivity, plus the derivative of the magnetic field as a scalar over time, over the derivative of time. So if I look at what you've written, you've got 4 different equations.
Yeah.
The derivative of the dot product of the B fields equals, what is that? Mu is the
I have to
permeability.
Yeah, if you want to put it on the screen, you can look at it. If you want to.
Oh, would that help? Yeah. Okay.
Yeah.
All right. Let me focus on that then. Where are we?
Yeah, presentation. Yeah.
Okay. Okay. Yeah, I'm gonna do that now. Present. Share screen. Share screen. Window. Yes. You can see this.
Yeah. So you come. Yeah.
Okay. Now, so we have the, what is this? The grad, or sorry. No.
Yeah, the del. Yeah, del dot.
Del time.
Dot B, the magnetic. That's what you call the curl and the the other one is
the gradient.
Yeah, the first del dot is the gradient. The other one is the
curl.
Scalar. Yeah, this becomes scalar. Yeah. So one is scalar, one
is a vector.
One is a vector. Yeah.
Yes. Okay. So, right. So I'm just wondering, because what you're doing here is you're saying that the monopole has no electric field. Yes.
Yeah.
And why is that? Is that because if you have an electron, are you saying that an electron has, if the monopole is the opposite to an electron, if you will, is that true?
No. The thing is, the monopole has only magnetic in a static sense. But when it starts moving around, it starts creating the electric field, because it has a magnetic. Yeah.
So why doesn't these equations don't deal with it in motion then? Is that correct?
No. For the this is a static equation, but when you put it back in there, put this back in there, some of them, like in the Maxwell equation, the Gauss law, del dot B is 0. But in the case of, if the monopoles are present, they are not 0. You see that? So, so that's how it changes. But the del dot E is based on the density and things like that, and the electric permittivity. That goes for the that one. But what changes is the Gauss law of magnetism is what changes for the monopole.
Gauss law for magnetism. Yeah, I mean, because you have like this.
Yeah.
This is the same as this, but this says 0 and this says
that's all. That's the main difference.
You're right. So that's kind of strange enough, but if we go here, so what I'm saying is that when you have the magnetic monopole moving around, plus this charge density, and I assume it's permittivity.
Yeah.
This equals an electric field.
Yeah. So you can substitute that value. You can substitute the del B, del T from that equation that I have, the modified thing. You can put the value of the del B. You can calculate from there.
Okay. Right. But these are very different equations. All of these to this.
Yeah, you have to simultaneously.
Yeah. What you need to do is, what I need to see, I guess, is like this converted into that somehow. Yeah. And then does that equal this?
Yeah.
Because if they're not the same, then either this is wrong or this is wrong or something.
So you have four independent equations and you have to solve them together. That's all.
Oh, okay. Well, do you want to do that now or?
Yeah, I mean, we have to figure out. I mean, this is a little tricky, but I think I can think about it and I can let you know how we can modify that. But your equation may be okay,
Well, that would be great if it was. Yeah.
Yeah.
I do that.
You will be okay, but only thing is that the B value will change. Will change.
Well, if this is this is a vector or something here.
Yeah, that also changes. So that vector becomes a little complex, and this one or del B also, del T also becomes a little bit more complex.
Well, this is not a vector here.
That's a scalar. Yeah.
Yes.
I think so. It's a scalar.
Because this is just the straightforward equation for not curl, but or no.
Yeah.
Right. And then this one is, well, it's not so straightforward, but it's not, probably isn't, excuse me, it's not that complicated either.
Yeah.
I would say. So I have a little bit of a cold here, so sorry for that. So that's really it. I mean, well, there's a lot to this. I have not been able to produce a slideshow in time because I'm very busy with assessments and coming back from China. So, but next week I have the assessment. Maybe 2 weeks, 3 weeks time, I can. Oh no, maybe actually next week I can. I don't know. I'll have to play it by ear, really.
Okay.
When I can do it, when I can't.
So you presented your PhD, right, in the conference? Your
a part of it, yeah. Okay. but quite an important part, I guess. So.
Oh, that's invitation. Is it like the invitation or something like that?
No, it was on. It was on Q learning as a means of anomaly detection. So it was quite good. I mean, it was a competition, so we had judges judging the work.
Yeah.
And I didn't know that it was a competition or that there were judges. So I was just.
Oh, you had a poster? You had a poster?
Yeah, exactly. They were judging the poster and everything else.
Presentation.
Yeah, the presentation. So but I didn't know that they were judging it. So I was really relaxed. I was like asking people questions about their work, and while everyone else just they weren't saying anything like. And then it was only afterwards somebody told me, "Oh no, those two people were the judges." And I was like, "Oh, okay, that's life." But yeah, so I haven't heard anything back from them or anything. So I don't know how it's going.
There were many people, like 100.
Oh yeah, there was a lot of different. Hang on a sec, I'll just check. There's. Okay, I can't lay my hands on it now, but there was all these different. I'm gonna stop. There was a lot of different. Disciplines at it. There was stuff on climate change. There was stuff on with the stuff we were doing, disaster, urban data and disaster. There was stuff on landslides, earthquakes. It was a whole load of stuff. A lot of stuff that was satellite based. So they talked a lot about something called SARS or something, which is and SARS. Apparently, they can measure like the height of water to within millimeters and stuff using these satellites. Pretty amazing what they can do.
Wow.
Yeah. So I was surprised. I hadn't heard. That's not really. NSARS is not really my area, so I didn't know. I'm more with Swarm and that group. So it's very interesting though. But I think it was pretty. There was somebody else working in magnetics, and there's a couple of people working on different areas of earthquakes, specifically to do with elastic and inelasticity of the crust and all this stuff. That is really like, there's so many little areas that you can research, and I'm like in a different sort of and the people who are similar to me that are also looking at maybe electric fields. Everyone just has there's slight differences with the projects that make them very different somehow. So like I know nothing about what they're doing, they know nothing about what I'm doing. Research-wise, we're just worlds apart. Might as well be. So, but yeah, it was pretty good. And then to China, we were in Inner Mongolia.
Oh,
yeah, it was pretty intense.
It was not Beijing; it was Mongolia.
That's right. Yeah. Well, we landed in Beijing. Then we had to take a train to Mongolia.
Oh.
And
was it a week long conference? 1 week.
Yeah, it was a week long. Well, maybe like Monday to Friday. I think I landed. I think I missed one. Yeah, I would have landed Monday morning, and by the I didn't get to Inner Mongolia until like 11:30. So I missed the first day. But and I thought I'd also missed the presentation. So I was like, oh right, I have nothing to do this entire week. This is great. But then no, but the presentation was the next day. So I just did that the next day, and then I took Friday off because I needed to explore the city.
How is it, Mongolia? How is it? I mean,
yeah, it was really nice. I went to the Dazhao Tibetan Buddhist temple, and I had a translator with me and everything. So, because there's what do you call? They have tour guides, but they don't speak English. But I mean, you wouldn't even really need a tour guide there. Just the experience of going and seeing the priests doing all their stuff, and then there's just the lay people as well going into worship. and these giant statues. You know, they're really impressive. Just the whole thing, the incense and the flags, and the architecture is very decorative. And there's an awful lot of like rituals and can't step here, can't go there, can't take photographs here. Very intricate and elaborate, like compared to, let's say, Catholicism or any branch of Christianity. But I would say, you know, just sticking to Catholicism, because I mean, Catholicism has a lot of bells and whistles to it as well, but it doesn't have quite so many. It's not so elaborate. Like you go visit a church, it's usually one building. You walk in the door, walk around, and then you come back out. But here it was like one building and then a different building that has a different function, and you're not allowed in this area of the complex, and blah blah blah. It's just very overly complicated, and I think that is indicative of Chinese society as a whole. It's just everything is, it's like here, but then they just add extra stuff so that everything takes more time and becomes more annoying.
Oh yeah, but it's nomadic, right? It's nomadic people.
Yeah, no, I met the guy I met there. He was my translator. Was such a nice guy. He's he was nomadic, and he was like just very. He was the nicest person possibly I've ever met.
Wow.
But I also like the but very different to a lot of the Chinese people that you meet over there, who are quite. They're not. I would have thought of them as reserved based on the Chinese people that are over here, but they're more. They're very animated, but then when they see you as like an outsider, they're like, "Who the hell are you?" And, yeah, I don't know what's going through their mind. I just can't read their minds at all. So I don't know what to say is going on there. But it's a strange experience.
But they're not xenophobic, right?
They're not I'd say so. Yeah, no. There's a whole thing going on over there now where if you're American and you're living in China, and like, let's say you're important as well, you're CEO or something, you could be, you know, the police could come in and raid you, and they're quite concerned about spies and stuff like that. So no, I'd say they're quite xenophobic. I mean, that's another thing. The whole conference was in English, right? Because science is kind of done through English internationally. And that makes sense. Like a lot of things are obviously, you know, you need one language because there's so many different languages. Then in China, the government are telling people don't learn English, just learn Mandarin Chinese. Because, of course, in China, there's all these different languages, isn't there, and cultures. So to unify them all, they have one language that everyone's supposed to learn. And, you know, we already have that for the entire planet. It's English. So... They're like, well, why do we have to learn this second language to communicate with everyone else? Well, that's up to you, I guess. But yeah, it becomes very insular. But one thing they do have that is new and that people are obviously using all around the world probably is translator apps. So, you know, you can communicate through the phone now, and technically they don't need to know English unless, especially if they're not going outside of their own country, which is probably a fair percentage of them. Certainly if you work for the government, I was told that if you're a police officer, for example, you're not allowed out of the country because well, this is what I was told. So someone else could come back and say that's not true. And also, I've heard reports that the Chinese are opening police stations in all different countries around the world. So there's a Chinese police station in Dublin, for example. There's a number in America. There's probably one in Germany. And they say, no, these aren't police stations. And they have a big sign up behind them saying Chinese Administration of Police. So, yeah, this is the way the Chinese are. Or, well, I guess. I don't know what they're like at all. I can't read them really, but they're mad as a box of snakes or something. I don't know.
So Chinese government controls Mongolia?
Yes. Yes. And they're like, you're not allowed to speak. You're not Mongolian, they're saying to them. You're Chinese now, so.
Wow.
So it'd be like if you went up to Canada and said you're not Canadian, well, that's probably not a very good example because Canadians and Americans are quite close.
No, the Queen is the figurehead of Canada, whereas America totally different. You know, the US is totally different.
There are differences, but there's a lot of similarities there as well.
Yeah, there are a lot of similarities. Yeah,
you're all American.
Yeah.
That's what I'd say. I mean, obviously you've got French. I suppose, yeah. I mean, I'm trying to think of a. No, I'm trying. I can't really think of an example, but so they're basically coming over and sort of shredding their identity a bit and saying you're not allowed. Well, I think they can still speak their language, but they don't want them to identify as Mongolians anymore, just as Chinese. So yeah, it's going to be difficult for the Mongolians, and as you can imagine, like.
So yeah, they were conquerors, right?
It's an unusual situation, though. I mean, can you think of any other country that's doing that at the moment? I mean, obviously, back in the day, the British, but that was hundreds of years ago, so we won't go into that. It's like, excuse me, ancient history is effectively, but this is happening like today in Mongolia and in Tibet and wherever. I think that, well, they want to attack Taiwan as well, but. I mean, that's unlikely if the US are there.
Yeah, Taiwan will be a big World War III, probably. Taiwan.
Yeah, because I mean, to do that, you're attacking the supply chain because they're like the major producers of semiconductors. So
yeah,
yeah, you're declaring war on the world essentially if you do that.
Mm-hmm.
And poor China then are cut out of these supply chains, but apparently they've started producing their own 7-nanometer semiconductor chips, but they're using American technology to do it. They're still about 5 years behind the curve, because what are they at now? 2 nanometers, or I think they're even getting down to 1 or something ridiculous like that. Although I thought they'd be way past the nanometer level by this stage. But there you go. But apparently, yeah, so they're behind in technology a bit now because of these sanctions and stuff. And I can't really say much more, I don't think, about the situation.
But
I don't know a huge amount about it.
Although
I will say, they are always talking about how the Chinese economy is kind of crashing. And when I was over there, certainly I think internally their economy is still working fine because they have so many people and so many shops, they can just continue to move money around and do their daily thing, whatever that is. But I did notice then when I was in Hohhot that a number of shops had closed down in the city center, like big shops. That would have been Apple. But then there was like 2 more Apple shops across the road and one up the street. So it didn't really matter. It didn't seem like they'd pulled out unless the Chinese had opened up their own shops and stuck a big Apple sign up in the front, which is very possible and very Chinese in a way. But then there were a number of other big shops that had closed. But then I also noticed that there was a massive mall that had closed, but I noticed subsidence underneath the building. So, and then I noticed that there was a subway station opening on either side of the building. So there was obviously a subway that runs underneath the building, and then that had caused some subsidence, so they probably closed the whole thing. But then when I was trying to leave Beijing, I had to get out of the subway again to go look for a bank. And there I did notice large, I don't know what you'd even call them, like shopping centers, and loads of closed shops around the outside. So it looks like a lot of Western businesses have pulled out. So maybe Beijing isn't that affected because it has such a strong home-based economy. But I hear like places like Shenzhen. Is it Shenzhen, the one near Hong Kong, and plenty of other lower tier places that, well, not that Shenzhen is lower tier, but so there's a lot of businesses moving out of these places. That's what I'm told by the internet. So, but I haven't visited those places, so I really don't know.
What is the name of the city? Are you okay? You are okay?
I've got a really sore throat for some reason. I might go get a drink of water. Back in a second.
Okay. So that's interesting, Christian. So do you have a chance to see whether you can do the iSpace for the false vacuum that we talked about? at the end of the last one. You know, the proton could be part of the false vacuum, things like that. And then electron may be in the true vacuum. And you can do a iSpace analysis of that if that's possible.
If anything is in with differential equations, which is not solvable multiplicative way, then I think I cannot do that. If anything is like in the recent document from Stefan Kühn, which I showed you last week, can be converted. So in other words, the theory guiding the magnetic and electric fields like Maxwell equations look complex, but they look only complex in this differential or integral form, which also Christopher has just shown that you can convert that. It's just algebra, in a sense, high algebra. And when you find a solution to this equation, you cannot know whether they are first order multiplicative or not. If they are not first order multiplicative, then they still contain some differentials or subdifferentials because you have partial differential equations. You don't solve it in a hop, in a swallow whoop for one thing at a time. So only for one variable. And that I cannot fix, or I cannot judge, to put it this way. I mean, when I was very much younger, I've studied physics for 2.5 years around until I gave up and made myself self-employment in the IT. Or I was always self-employed in the IT, but I studied parallel electrotechnics and then physics. And I was fully happy with this, but I couldn't live from that. So I just, for more or less pure aggressive monetary reasons, I moved into the business of being self-employed in the IT, and I was very, very successful at the time. So I didn't look back and say, should I have done physics studying because I really love that, or should I have done electromagnetics, electrotechnics study like Gerd is a true, really, really a full expert on. And what I learned is that my mathematical instinct and capabilities is not on the par of the level of the people I studied with. So during my time at the TU Munich, I learned in these work groups that you have where you sit with 40, 50 people in a smaller room and not on the professor level, but usually the doctor degree level when they teach you these kind of things like running Maxwell equations properly. I never felt at home. But this is to say, I felt at home when I was in IT, in the sense of having studied computer science. But computer science in its own is very mathematical, and this is also not what I wanted, or what I have talent for. What I really have talent for is assembly programming, or hardware, or binary logic, or going to the deepest level of details of anything. And on that level, it gets binary quickly. And then you don't need anything that what I can do probably better than most of the professors in this field. So I recognized when I would continue studying electrotechnics, it wouldn't bother me because I was better than them, and at least in the sense of having real results where they were theorizing things, which is not wrong, but it was not helpful for me and the customers I had, not at all. So I delivered things and was very successful in doing so. And for the physics, I was sad because I was aware that many friends of mine, like Harald, very, very talented physicists, already at school. So they really had that talent, and I never really had that. So what I'm really talented in is informatics, in the sense of the lowest level, building computers, building low-level operating systems, porting hardware, Internet of Things, as you call it today. But at that time, it wasn't a word for that even. I was more like low-level IT mechanics. And what I saw there is that all the equations you have in the electrical area were very, very similar than that in the physics. And the physical equations, in turn, what I learned later when I was at Wolfram Research, were very, very similar than that at what is the commercial equations. So then when goods travel through the world and get sold and stockholder value and all these kind of things, they have more or less the exact same equation machinery behind them. So there seems to be a universal from nature guided principle of nested hierarchical structures, which are in turn guided by differential equation at first sight. But when you are able to solve differential equations, for example, in the sense for constants of nature, as I did in iSpace, this was a very weird abstract mathematical model necessary to get hold of that. To get out of the accusation part of numerology. The result would be the same even if I just throw the numbers over the fence. But if you don't have a model for that physically, then nobody's reading your papers and nobody is just talking to you even. And learning that these structures could be simplified, my really hope is that the differential equation mathematics in other areas can also be simplified in much the same way once some with a tremendous more insight from two fields comes into that area and simplifies it. I think you need areas from two fields. My IT helped me much to understand these square circles of size space, because it is quite that what you do when you have digital pixels on your screen. And when you program graphics drivers for screens, you suddenly learn that everything is discrete because it needs to be. And then you can take your conclusions how to implement certain things. And I think the mathematical background of physics is overweighted in the moment after 120 years, especially since theory of relativity and theory of quantum mechanics started there. I'm reading a lot of papers in ResearchGate these days where people going back from a Newtonian approach, not this kind of Mond or stuff of Gerd, so really much more basic, even having looking back before all that started and said, where did they deviate to the left when they could have gone straight or deviate to the right?
Right.
And I'm not saying that the theory of relativity is wrong in any way, for example, but I'm saying the approach of thinking of a bending space-time is fully incompatible with iSpace, and iSpace is knowing that you have a quantum of time, and absolutely sure on that, which means there are no varying time. So you need to find a mathematical model which gives the exact same results of the theory of Einstein on, say, 11, 12 digits after the comma, or you're not taken serious, without assuming all that four-dimensional geometric bending. I believe, for example, that everything is, or not, I do not believe that, I know, I'm absolutely sure that gravity is a force. As like electric forces are not negotiated by physicists. They have it every day in form of magnets, little toy magnets with their children, little magnets on their fridge, little magnets everywhere. So they really seem to understand that that is too simple of having a high-end explanation other than that what is known with the Maxwell equations. But the Maxwell equations are just a piece of mass which are extremely high level. They describe a lot of things, and if it can be done easier, that remains to be seen. Now, Steffen Kühn has now a solution for the Maxwell equations, not making them superfluous, but at least allowing them in a multiplicative way to be 1,000,000 times faster calculated. And it tells me something. I always was discussing with the high-level physicists which I met in my life that God is too busy to do algebra. Yeah? He will invent a schema like Lego which just works, where you need to count things or just have things automated. And these complex mathematical stuff is often including when complex numbers are derived or infinity is involved, often the zero is involved, and all these kind of things lead to edge cases which need to be explained. And suddenly you have a black hole which has infinite mass at zero length, where really every scientist on the planet who steps back and says, yeah, that can't be. It will not have zero size, and it will not be infinite mass. It will be the whole mass of the universe maybe in one black hole, but even that is not infinite.
Yeah.
And the mathematics is invalid in these areas. And as it's invalid, my assumption of all these equations you started the session today with is that they are approximations. And when they are approximations, they are valid over a very, very wide range, but not when you look deep. So close to infinity or close to zero, they're wrong or getting wrong. And it depends on your unit scale of your unit system chosen to see that. And my insight in iSpace SI, so compatible to MKSA SI unit system, was not so big 15 years ago when I published my papers on Prague IMS 2015, but today they are. And I know now so much more on the interpretation of what I calculated 15 years ago, that I'm sure that it is all just blinded by mathematics, what we have in physics and problems today. And this blinding by mathematics doesn't mean that mathematics is a bad tool, not at all. But it is a tool and nothing more. It is never the truth. And the people are like in a church. They're praying relativity like, if that breaks down, we will all die. It's like, no, we won't. We're just back at Newtonian mechanics with a little bit addition, which we don't understand to do yet. Now, nothing will happen. Nobody will die. And but world models will die in the sense that everything you learned at school for the last 100 years plus will be wrong, and new books would have to be written. Would that be really that evil? It's like, this is scientific progress.
Yeah, very true. Yeah. Well, what do you think, though, is correct from the theory of relativity?
The results and nothing else.
Oh, okay. Yeah.
So the mathematical precision with which you, for example, I have talked with Walter, my physics professor was the father of the CERN CMS. So who am I to argue with a person like that? It's like talking to a Nobel awarded person with 50 years of experience in physics.
Yeah, I understand. But okay, let's say you know the muon experiments in the colliders, or the particle accelerators. Sorry. And
yeah.
they put them in. They put in like silver ion atoms or whatever, and they send them around at light speed, and they tick slower. So
yeah, they do. So the destruction time of radioactive particles or muonic particles, which have a decay time in general, because they are not stable. And even for the proton, there is theory that the proton is not stable. But with all due respect to these people, get a life and respect that electron is stable, positron is stable, and if I'm right, everything is built out of matter in the sense of electronic and positronic combinations. If you call that a proton and make it magic by some color quarks and all that, is again just a model. I calculated these stuff from other.
Just to get a quick answer on the question. So if you're saying that time doesn't bend, now based on
this is what I'm saying.
Model, well, just the model I'm working with has no relativity in it. I can't find special relativity in it. You could probably work it in, but I think it would start getting kind of messy. So I like the model.
Sure that you have not hidden gamma factor somewhere indirectly? If you have a equation where c squared is over something squared, you already factored it in one way or another, just as an example.
Well, I'm talking about more like, the way you have Galilean relative, like that kind of special relativity where, simultaneity breaks and lengths get shorter and time expands. I'm not discussing like the mass, the E equals mc squared. I think that's probably valid. But I don't think the theory, I'm not sure if I'm saying this right, but stands or falls based on, I think they're two separate things that could exist. Like special relativity could be proven false tomorrow, but E equals mc squared could still be valid.
Special relativity is very much verified in acceleration experiments of particles, which are unstable, and the times with which they decay statistically, you repeat the experiment 1 million times for 1 million particles, and statistically the result is way beyond 5 sigma, that you get a decay time proportional to the proper very exact equation of Einstein's relativity. There is no doubt about that.
Okay, but then, all right, sorry to put you on the spot here, but didn't you just like 5 minutes ago say that time cannot bend in iSpace?
Yes, so that means the model of relativity is wrong, not their mathematical equation. It's a model. And it gives us this very weird mathematics, the right results for the decay time. What you have to find is the true equation for a model which is Newtonian anchored, in the sense that everything, we have a flat space, there is nothing bent. It works completely different, but the model to make it work completely different will be from the equation of iSpace, a 10-dimensional spacetime with 6-dimensional subspaces. We will have probably propagation larger than the speed of light, very likely, not because I say so, but because the the Earth as a planet would not be rotating around the sun on a stable orbit over 5 billion years, would gravity be indeed blocked by the speed of light. There are calculations, simulations on that, and the moon would have left the Earth in orbit billions years ago already because of mass instability. So if you have 3 bodies and they surround each other, you get non-solvable exact. Oh, I'm very sorry. I have to stop that.
No problem. Okay.
Sorry, I forgot my ringing off. Very sorry.
No problem.
So I'm just saying that the model depends on the thinking. So when you start with theory of relativity is completely correct on the right hand, and with theory of quantum mechanics is completely correct on the left hand, and you have experimental proof for both of it for people who are not stupid, then you have 2 sorts of people, some of which say both sides are correct and said you're proof, then please combine relativity with quantum mechanics that we were not able to the last 120 years, then something is wrong, right?
Yeah.
And nobody is at the moment disagreeing with my instinct here that something is wrong. The question is which side is wrong. Is relativity completely wrong and quantum mechanics completely correct? Or is quantum mechanics completely wrong and theory of relativity completely correct? Why are they incompatible? And they are incompatible because you look at the math. Look, it's simple. Let me explain with a simple thing. I need 5 minutes maybe to breathe in here. We have the speed of light is constant, has a unit meter per second. And we have the Planck constant. In iSpace is now shown to be absolutely constant. There are other theories which they can vary, blah, blah, blah. But assume for a second it's constant because it's a constant of nature and it really accept that iSpace found the true relationship. Then you have an equation with the unit volt ampere second squared. So you have 2 times the iSpace quantized second in the Planck constant, and you have 1 time meters per second in the speed of light. And when you combine those properly, you get a force by volt ampere second per meter. Now these seconds cancel out, but 1 second in all these equations stays, which means that force is quantized natively by this design in quantum mechanics. You have h as a Planck constant, and if you do a h bar and make it rotate or not, doesn't matter for the argument. Energy is quantized by h. Speed of light is constant. Both are parts of relativity, if you want it or not, because the energy in relativity is also the same energy as calculated by the Planck constant. Energy is not continuous. And the theory of relativity treats everything continuous. It treats the space-time continuous, bending by masses, but the masses are constituents of energy which is in one way or another accelerated by the speed of light. Otherwise, the E=mc squared equation would be nonsense. And it's not nonsense because it's experimentally proven also. So whatever you do there, on the left hand, you have exact time in quantum mechanics, and more indications show that while it is a weird theory with a weird virtual particle system, might be fixable by iSpace, where all that weirdness goes, would you see the proper math. Assume for a second iSpace would in the future be able, by people with better mathematical abilities and better physical knowledge than me, combine iSpace and quantum mechanics to something really simple, then that virtual particles might even go away. And you really have super simple things on the left side, and everything in relativity on the right side is built by the super simple things on the left side, right? Or wrong? Yeah. So if that assumption is right, that everything on the right, all masses of all planets are made of atoms by rules described by the quantum mechanics, then quantum mechanics is in relativity if you want it or not. And if you choose that you have a quantum of time on the left side, you have a quantum of time on the right side. What we can argue now is there something in these cells of space-time which can bend? When you have a speed of light in a vortex where you do your monopoles, for example, Rajan, which I really not fully understand, and you have a space-time of these cells, the cell diameter could change, for example, with the mass. It's just an assumption like anything else, but it is guessing into the wild. But this could be a discontinuous thing when you have a whirlpool and the rotational diameter of the whirlpool in a pool of water style energy, subspace. And the rotation of the cells would limit the speed of light going faster than anything like that. And with the model of Emmanuel, again, other type of waves, longitudinal one, could go much faster. That would explain by the gravity, which I have in, I think, 2 weeks ago shown the equation where I derived the G from epsilon 0 and mu 0. And both are exact in SI unit system until 2018 at least, which implies G is also exact. No way, because just integer multiplication and no tricks, no gags. And it was completely plausible what I had as a result. And one of that results was a speed factor. And that speed factor had meters per second with 10 to the power of 19. Now, that is a speed of gravity, which I say makes sense. Nothing like that is theory of relativity predicting. Theory of relativity needs 75% dark energy to survive. Where is it? I haven't seen it. It needs about 22% or something like that of dark matter to survive. Where is it? I haven't seen it. Is it subspace? They just invented to fix their model, or it is completely wrong. Yeah, wait a moment. The last time I looked, when something like that is wrong, it is completely wrong. Nobody would hold a model up to that. We need 75% correction, not 0.075% correction, no, 75% wrong. I would say, come on, something really we need to talk about again. Let's start from scratch and follow step by step. What did we discuss the last 120 years? This is all what I want. I want to go to the experts and say, let's go back to the time when Albert and all the others, Bohr and Heisenberg, were alive, and said, let's settle that. They were at the Solvay conference and they settled it one way or another. And all books after the Solvay conference were, say, quantum mechanics is don't shut up and calculate, don't ask why it's so weird. And geometry of relativity is we have Minkowskian spacetime, don't ask why, just learn the complex math and keep our shut. And what I'm not saying is that this math is wrong. What I'm saying is the whole model using the math is wrong. With this math, you get proper results up to some point, but not for all your results, just for very specific experiments. And today it seems, and the people choosing these experiments intentionally in a way that they never choose an experiment which falsifies them. They seriously research on something to have more precision after the comma, but not look at the big thing. Big thing is, what the hell is the 75% dark energy? I was in a meeting of Siemens Stiftung 4 years ago, where they regularly invite me and Harald to were very grateful with the best physicists around Munich and sometimes the world invited there. And there was an expert of gravitational simulation from the University of, not say it wrong, it's the Albert Einstein Institute in Potsdam. And he was the lead of simulation. He is the world best expert. I don't remember the name right now. I'm not good in this name remembering, but you can look it up. And he was showing the best simulation he had for what stars do after the Big Bang automatically, how they form galaxies, how they form all the structures and things we see from a Big Bang assumption. And the Big Bang assumption is even a problem because the Big Bang assumes a high speed over the light inflationary phase. So you have to fine-tune that. So how long was your inflationary phase? And you cannot measure time there because time is something where you need space to measure time. But during inflation, you have not even time because it's superluminal. Superluminal time mathematics is invalid before having that. So they assume something. When you want to have more details on that classical style, please read the book from Steven Weinberg, The First 3 Minutes. It's a very short book, but it's really completely telling you how it is viewed from today, what happened the first nanoseconds for inflation from our point of view, then all these graphs where you have this bowl going up, then spreading out, where the universe has become bigger and bigger. Nearly every Scientific American second volume has a picture like that somewhere in one of the theories. So it's really nothing new here. What is nothing new is that all these images don't explain the 75% error. And when the simulation came out, he showed us in a 1-hour presentation how precise the galaxy structures like the telescope. So he showed the simulated images and the telescope images at different distances. And it was really brilliant. So all the structures at the right distance from Earth showed the correct or optically similar structure. So the simulation was far from completely wrong. And when we were standing on the, after the meeting at the table, by coincidence, the two professors, which I know of, and him, the presenter, and me were standing on the same table. And I was for about 20 minutes watching all their questions, and they were over my head. So they're really discussing very complicated things of relativity and space-time. And when all the questions were gone, he approached me and said, "Do you also have a question? Who are you?" And so I introduced myself, that I have a theory of iSpace, so I can calculate constants of nature. But I'm actually an IT expert, and he lauded that. He said, "Yes, IT is the most important thing for simulating that for supercomputer, blah, 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 C++, whatever." And I said, "I have only a very simple question. If I would have a theory which gives the right results optically and needs a multiplication with 0.75 to get the right results, I would write next minute a paper that, hey, we have a near complete theory. Unfortunately, is wrong for more or less exactly 0.75%. Why is that?" Then he laughed. Yeah? So he fully understood that he had to fix his model showing the right distance for all the galaxy structures from near after the Big Bang to today. Then and only then, when he assumes 75% dark matter or dark energy or whatever. And what I didn't know, but could laugh myself after that, said they multiply it into the simulation. So you have man-months of supercomputer calculations for all these images, and they are completely wrong. Would you not just take multiplicative correction by 0.75? Now, that is what I call in my world a wrong model. Sorry. Yeah, it's that simple. It's just, you cannot say, well, where is that 75 from? No, if we don't multiply by 0.75, we don't get the right pictures. Ah, so, okay. And what is the factor? What physically is it? We have no idea. We call it dark energy and dark matter. I say, thank you for talking to me.
Yeah.
This is silly, and this is what they need to get. I'm not saying that all they're doing is wrong, or what they. I'm not also in the lager of that. People who say all of people who love relativity are just a mad sect like a church. Yeah. They want to protect their theory. They're really clever and they know what they do, but they are in a sense desperate. They're desperate. They see more and more results of experiments around them which don't get justified by the classical, need more and more correction factors. And there needs to be a thinking from a new group of people like maybe us, a new generation that says we are not afraid of being wrong.
Yeah, that's true.
And we're not afraid of telling just one day the perfect theory and the next day the complete bullshit. Because it was what A was just an idea, was coincidentally right, and B was just an idea, was completely wrong. Doesn't matter. We talked about that is the most important point.
Yeah,
we learned something from each other, and that is so cool. We are not afraid. Otherwise, we wouldn't make live sessions here.
This is it. Recently, I wrote 2 papers, and well, I wrote 3, and I thought I'd sent the first one off. So I was like, oh, maybe I should send the next 2 off as well. But I'd actually made an error. I hadn't sent the first one off anyway. It doesn't really matter. But I sent the other 2 off, and then I got a reply back pretty quickly. Like, they were like, I talked to the board on our paper, and we all agreed unanimously that these 2 papers are against the theory of relativity, and no serious journal would ever publish anything against special relativity or what have you. So yeah, we rejected these. Don't bother sending us anything like that again. And I was like, you know, like I wasn't aware that that was a thing, that they wouldn't publish criticisms. But even in the paper, like I made, you know, I would always say from the perspective of my theory, this doesn't seem to be correct. And there was another point I made about Einstein, like just how do you say, like he basically asserted that his theory was correct, even though it was against everyone else's understanding like, oh, space can't contract, time can't dilate. But he just said,
no. That he has in the end of his life papers that were contradicting his own initial thoughts. He got the Nobel for. No, the Nobel he never got for the theory of relativity. The Nobel he got for the
well, just the point, like, so before Einstein was even like in college, even they were talking about relativity, you know, classical relativity with I can't remember. Poincare probably and other people.
Galilean relativity and the equations were there. They're
well, even, you know, because the experiment, the Michelson-Morley experiment, was done in 1890. So I think Einstein was about 12, and then so they were discussing it for decades before he came on the scene. And
they were also desperate. Yes.
Yeah, but yes, true. But
Einstein jumped in and helped him out of that despair with a theory which is more weird than their own one. Maybe like iSpace is weird enough to be taken by mainstream one day in the future, because they're so desperate that they don't have a way to fix quantum mechanics another way. And I will sit silent there, smiling, like, said, do that. I'm not saying iSpace is the correct theory. It's just a helpful, another weird tool of mathematics to calculate constants of nature out of nothing. And Einstein was very much, when you read the non-scientific papers about him, there's all on his webpage of the, where all the papers of him are collected voluntarily by the organization, with the Einstein Foundation. And it's very interesting when you look at his life. He wasn't the mathematical superhero or anything like that. The Minkowski spacetime is from named because Minkowski was good at math, and essentially
he was his teacher, right? Minkowski was Einstein's teacher.
That's what I heard. Yeah,
a professor. He was a professor. I mean, he learned mathematics from Minkowski. Was one of his advisors or whatever.
Yeah.
But that is what I'm saying. So the special relativity is Einstein's insight of simultaneity and what happens. And exactly when you look at the special theory of relativity with relation to cosmology, with the twin experiment and all that, you see a clock cannot be older and newer at the same time. This is just nonsense. People have to accept that there is special relativity is completely wrong with respect to that. You also not have a twin paradox. That is all not necessary. I read a lot of papers in ResearchGate about that from clever people who have better models, and untangle that over the last decade on what you have to do model-wise to not get the same results than relativity. There's not, the results are not wrong. The trick would be to find an experiment where the new models deviate a little from that of Einstein's predictions to prove once and for all that the Einstein equations, which are very simple in special theory of relativity, are not exact at 100% for all cases. They are exact to some whatever accelerator experiments where the mass increases with the rotation amounts over the accelerator. When it's a ring accelerator, then the more you accelerate, the heavier the particle gets. At some point, it has near the speed of light. It will then not increase the speed anymore, which is easy to measure. It will increase its mass. So you need to strengthen your magnetic field strength, or they will hit the curve of the accelerator. And all that is extremely well proven. But that doesn't mean.
To me, if that is all well proven and it's all correct and accepted, then I don't see the issue. Is it not just correct then at that point? Well, why do we need to tweak it?
The issue is that if you have a quantum of time, it cannot bend. That's it. And that's a big issue. So what the hell makes the time deviation geometrically?
Yeah, one of the things I found that the time, when I did that all the math, the time in the quantum level up to about half a kilometer or so is linear time. But above that, it's non-linear. So that's the problem. I think in quantum, like what Schrodinger is saying, that's a linear time. Whereas in the Einstein thing, it's not non-linear.
That would much fit to iSpace theory. This is also my idea. In subspace, in the 6 subspace dimension, you have linear time is quantized, And all experiments measuring the very, very small measure not space and space-time, they measure subspace, because the atoms and particles are made of subspace. And hence all their quantum mechanical experiments show the right results, because they only look at 10 to the minus of power of minus 12 meters. And there is everything as it should be. It's quantized there. And if you look the very large, the cosmology, then nobody would have thought before iSpace theory that G could be constructed from quantum mechanical constants. But that is easy, as you have seen. It's not even irrational in a sense that I need far-fetched assumptions. I do very, very simple things geometrically. First-hand multiplication, I can construct a G, get the Hubble constant of that, and all is exact. I was like, it cannot be a coincidence. I have the translation factors, which are not just arbitrary numbers like in a physical experiment where you measure something and you suddenly invent a constant k or dashed k and say this is 7.57573555426 something, and when you apply this multiplication, then everything fits. So, but you have no idea why that constant needs to be applied. Is a constant of proportionality. You need it, but you have no idea why. You measured it, and that's it. And your linear fit in your curves of measurement showed you that constant of proportionality. And iSpace theory does nothing like that. It predicts you firsthand what the forces will be. And that implies that the geometry of relativity is necessarily wrong. In my papers of 15 years ago, I chose a hybrid model. I left Einstein alone and said we have four-dimensional space-time. As it is, because I didn't want to write something which would affect 15 years ago the people of relativity against me. I wanted to show something new and said how to make that the best way. Show them six-dimensional subspace, Calabi-Yau spaces, show them the mathematical reason for that with a new geometry, show them that constants of nature arise, and leave relativity where it is in the other four dimensions. But today I cannot do that anymore, because I'm now aware of the quantum of time. As long as I talked about the magic 6961 number, which I didn't understand, I had no argument against or for relativity. I said these guys know better. But now I'm absolutely sure that is the quantum of time. And when time is quantized, everything is quantized. Mass, length, energy, everything else is quantized when time is quantized.
Well, wait, are you saying that well, I understand what you're saying there, but like when you're talking about a quantized time and you have this number, are you saying that that's equivalent to like absolute time or
absolute time? Yeah.
Oh yeah. It has to be absolute.
Absolute quantum tic-tac time. Not bendable, not changeable. Nothing in subspace changes time because you accelerate a spaceship to half of the speed of light. Nothing. And why do we know that? Because when we're inside that spaceship, we breathe normally, yeah? So the quantum and the breathing is the same. And what the theory of relativity tries to tell us is when we fly to another star and come back, we are very old. I said, bullshit. It's just bullshit.
If we were
experiments proving that our quantum experiments, we haven't built a spaceship and fly with half the speed of light somewhere in a jetpack.
What I'm saying is that if we got in the spaceship and we left Rajan here, we went off to fly at the speed of light and then we came back, we'd be younger, yeah? Rajan would be older?
No, we wouldn't.
No, we would be younger. No, according to the theory of special relativity.
Yeah, according to relativity, we have the twin problem then. And the twin problem is mathematically induced nonsense. It is by the models. This is one of the weak spots of relativity where they won't give in. Talk to them in ResearchGate all the day if you like. I'm following this ResearchGate discussions as good as I can. And I have not enough time to read all of that. Yeah. But I read what they discuss there, and they take a bloody X. Professor A takes a bloody X and hits in the head of Professor B and is happy to have the smallest. When he says something wrong, he has an X in his head. This is not science anymore. This is Christ-like belief. I believe the right God is the one in the Roman Catholic one. And the other comes, I believe the Indian guru is the right one. And the third comes and said, we have no church or whatever. We need to be atheistic. And all of them are right because it's just belief. Okay. I haven't met God. He hasn't ring my door and said, "Hey, can I help you?" So it's belief.
Yes, of course.
So and models are also just that. They make you believe that the model is applicable everywhere. But most physical models have an application limit. For example, when you have, I'll give you a super simple example. I talked when we were away last. I'm interested how you would see that. There's my example from last week.
Yeah.
Not sure you saw the video.
I did. I watched it.
When theory of gravity needs to be Einsteinian, one, then we have a black hole, and the black hole has all the mass in it, say, of a galaxy like M87, a really violent big one, a supermassive black hole.
Yes.
And the supermassive black hole will have the standard Chandrasekhar radius, which you can calculate by the standard equation. It will be millions of kilometers away from the point where the black hole mathematical center is, with the zero length in it. So from the millions kilometers away, it will look like smooth space. There's nothing visible. When there is nothing that the black hole can eat at the time, then your spaceship crossing that border is the only one in the whole universe crossing it. You will not notice that you just passed something which you cannot escape anymore. Okay?
Well, I'm not sure if I agree with that, but go on for the sake of argument.
Yeah, but this is a model as well. So, but anything inside is the mass. And if a second of that, so when this black hole has eaten up anything of the whole galaxy, you would be just a black hole invisible with the whole galaxy in it in a far future from now. Now assume a second black hole did the same thing on another galaxy. Let's call them virtually M89 instead of M87.
Okay.
And they're moving slowly towards each other. Both have swallowed everything, and they're drifting in a distance of 1 light year away with a speed of, say, 10 light years per year. And
okay.
How will they note each other that they are there? They would not even note they are there, because the speed of light will take 2 years going forth and back between them to inform them that they will cross each other. So they bypass in that distance and will not feel the gravity. They will be moving in a parallel line, bypassing each other before they can exchange the information that they should attract each other. They are supermassive. They need to attract each other.
Experiments then of like two rotating black holes, and
the theory of relativity tells you that the space bends, and the bent space informs the other galaxy that it must bend towards the other. But bending means superluminal. This is just another word for, with superluminal information, I tell the other galaxy, by having a woven space fabric which bends faster than the theory of relativity's speed limit tells you it can bend. That is nonsense. It's all about the information which is lost in the black hole.
See, one of the things I come up with...
When gravity is superluminal, it can easily escape the black hole and inform the other black hole. That is a much, much more suitable model.
Oh, okay. I got you. Okay. Go ahead, Rajan.
Yeah. So one of the, I think two things. One of them is, I believe that, in the quantum, like I said, it's linear, and outside is non-linear. And the reason is the time is produced by a body. This is what I come up with. Information comes from the superluminal. So your time, like our body, is the one that's creating time. And the superluminal is giving the information. So the information comes from here, time comes from here. Okay. So that's how the information is not necessarily limited by the speed of light. The information can travel.
Yes. This is information theory how it's applied.
Yeah, you just replace the clock by a superluminal clock. Would we be able to construct one? Then we would know if we could travel faster than the speed of light or not, and how to do that. But if something is physically able to pass information faster than the speed of light, then human creativity, one way or another, will, after some time, invent something to make a mechanical use of that.
Yeah,
and hence
gravity. Example, gravity. Gravity, like you said, is 10 to the power 19. So it's faster than speed of light. And the gravity is an information. So the gravity gives the information, instinct information. But the time actually, is developed from the body. So it's limited by the speed of light. So the information comes from the gravity. But when the time goes out, it goes out the speed of light.
So that's, I'm not sure I understand you. When you transmit information by photons, you send them with the limit of the speed of light. And what you're saying is gravity sends information also, but not with the speed of light limit, but with the speed of gravity limit.
Yes.
And it's the same form of information. It tells you some mass moved and hence some energy changed, and hence some gradient changed, and hence you can calculate that with theoretical calculations of Minkowski spacetime, but you can also assume just you reached the information and acted appropriately with your model.
Yeah.
So it will give the exact same curve of both bodies.
Actually, what happens is that, so the information is coming in for me, for example, at the gravity speed inside my body. But what I give the information out is the speed of light. So where does they come to the picture, or entanglement, so to say? So they may entangle at some point, and they limit the space. So I will know when I send the information, I get the information back because it reflects back to me, like a photon I send. And the photon reflects back to me from that interface. And you can see that mine is limited. I can see the sky, but I don't know what's happening beyond that. You know, what's happening beyond. I know up to certain level, like a half a mile or something, I will know. Beyond that, I don't know what's happening, because that information, gravity has, if the gravity is giving me information, that information, then, you know, I compare these two information that I create versus the information that's coming in. I compare these two information. I see a contradiction or limit. Then I know there is, you know, there is information. So I try to process that. You know, that's what we are. I think we are not able to really process that. I think there will be a model by which we can, once we understand this thing, once we prove it, there will be a model of information, whether they're the quantum, like dual information. It's not, one is coming into me, one is going out from me. So how does that, like I am telling you something, right?
Rajan, I think I agree with you that there is information exchange by gravity and by light style particles. Yeah. So that is one thing, but then there would also be need a field in a way of gravitons are measured to have a maximum speed of light limit.
Yeah.
So that we are not talking about gravitons. So they are superluminal gravity. We need a new name for that.
To have a speed of light limit if we've never actually seen a graviton before. Do you mean theoretically?
I mean, when something transports information, it is not relevant what name we give to this thing, but there will be not only one of them. It will be a flow of such particles, and they will need a name, and they will be form of field.
I'm just asking you. You said that gravitons have been measured to move at the speed of light, but
LIGO did that, because they saw the optical events of explosions in the telescope, and they saw the correlative events of the merger, which they predict with the LIGO interferometers, and that shows you that the signals came in within milliseconds. That means that they happened with the speed of light, the transport of that.
Oh, right. But that is a gravity wave. Is a gravity wave the same thing as...
Yeah, what else is gravity wave then consists of gravitons? What would you think it is? I mean...
well, I mean, it's meant to be a wave.
A gravity wave, an Einsteinian wave, is wiggling the manifold, yeah?
Yes.
But if a manifold is a fiber or something, what information tells the fiber to bend when the wave comes in? The wave in its own, like a soliton wave running over the fiber in a canal, when you can make a soliton water wave, gives you the information, wave is there or wave is not there. When the wave hits the wall, it reflects at the wall and drives even back until it fades out, because solitons are quite interesting waves. But whatever kind of wave you run in a fabric, it will give you information of the presence of an event. And that is enough. That is the information. So when the soliton wave passes you and you have a detector in your fabric that it passed you because it bent your fabric a little, and this is exactly what the 3 kilometer arms of the LIGO do. they measure the mirror distance gets spent by solitons run through the Einsteinian assumed fiber. So they shift the position of the detectors in nanometer area.
Yeah, well, yes. Okay, but that is still, I wouldn't call it like a graviton, though.
But this is what it is.
Okay. All right.
So the other aspect, the other aspect is that, so what we are talking about, the two types of information, right? But there's one more thing in that one. What I was trying to think was the graviton. Yeah, the graviton you said is limited. But what I want to say is that you had 6961, right? It's interesting because I calculated the time. Yeah, I calculated from discontinuum, physics that I'm doing with Emery Taylor. That has a whole new thing about the. When I calculate, I get 1 millisecond. Is like a constant. So it will be very close to what you are saying. So if you invert your 6961, it's very close to 1 millisecond, isn't it?
No, it's not very close to 1 millisecond. It's actually very far away. So the 6961 is not in SI system. The 6161 is in iSpace SI units 10 to the power of minus 19 seconds. So this is 10 to the power of 15 orders of magnitude away from your number.
So it is a different thing. See, 1 millisecond, it gives certain things.
Just for calibration, 1/6961 is a number in iSpace seconds. And iSpace seconds mean you're in the iSpace IQ unit system. And that can be lossless converted to SI. So when you have 1/6961 iSpace seconds, you have to multiply with 47 times 14.665,487 over 10 to the power of 24. And then you end up by 1.9 something 10 to the power of minus 19 seconds.
Right.
And that is iSpace base time in SI. And when you multiply that time with golden ratio ampere, you get the electron charge, which is surely no coincidence. Okay. So that is how electron event changes propagate with the time 1/6961, which is quantum physical time, and the human-made artifact factor 47 times 14.665,487 divided over 10 to the power of 24 is just formed by the SI committee unwillingly by defining the clock the way it is defined. It could have been another atom, it could have been another clock frequency, they could have chosen whatever transition frequency they find in any atom they choose, and you would get another human artifact factor. But I bet my ass that you would not see a different 1/6961. So the 1/6961 is quantum physics, so iSpace theory is the most bullshit idea ever invented on this planet. I stick to that. So it is so unlikely that that is coincidence.
What did you say there, Christian? What's bullshit?
iSpace theory is for sure too correct to be accidental. And when you look at the mechanics of iSpace, you see certain numbers, geometric numbers, integer numbers, prime numbers, and the 6961 is on the denominator together with golden ratio and pi. It makes the actual physics, whereas the human numbers are in the divisor. And the human numbers can be removed to 1 when you go to iSpace IQ unit system.
Christian, what were you saying was bullshit? Quantum mechanics? No, hardly. What were you saying?
No, what I'm saying is that if that is accidental, then iSpace theory is the biggest bullshit ever invented. It could be, but with what probability?
Why are you saying iSpace is bullshit? It's your theory.
Because it could be that it's just brain fuck. I don't know. I invented something, it gives correct results, but it can be accidental bullshit. Of course, it can be completely wrong. The probability of which it is wrong, this is the interesting question. You have to find an alternative theory which gives the same results than iSpace from a completely different mathematical background, be it quantum mechanics or theory of relativity. And then you compare what you need to do that, 20 years of supercomputer time, whatever. And I do some pocket calculator multiplication, get the same results. Now choose. This is Occam's razor, right?
Yeah.
So with Occam's razor in the hand, I say the simpler theory wins. And that is for sure iSpace. You will not find any theory which has a simpler equation for the quantum Hall effect.
The only problem I have with iSpace, well, Yeah, maybe the only one. You know, pixels, that's probably true, I think. But then the 10-dimensional, 6-dimensional torus thing, and then how the flip does that relate to all these constants? I just don't get that.
Space, right?
Sorry, what?
The electron has a number. The electron in iSpace theory has a mass, and the mass is 1111111.
Yeah.
It's a beautiful number because it is number 10 plus 1 times 10 plus 1 times 10 plus 1 times 10 plus 1 times 10 plus 1.
If that's similar to the iSpace units, is that also like 10 to the minus like 8 or something in if we were to convert that to SI units?
You can do that. It's all the time which is converting it, interestingly. The mass is not converted. If you look at the paper 1/6961 is the quantum of time as I published in ResearchGate, is a sequence of 200 equations which linearly take an hour to read, not more, not less. Go sequence step by step to the equation. The hardest thing you will ever do is a pocket calculator and multiply if that what I calculate there makes sense or not. If I made a mistake somewhere, I cannot make a mistake because I use Mathematica for multiplication.
Yeah.
That makes no mistake.
Well, wait a second, though. If you're saying that they don't convert, then you're saying that mass 11111 or whatever is
that is the electron mass. That is an integer. Yes.
But that's correct in SI. Is that correct in SI units as well?
If you convert it properly, and to convert it properly, you have to multiply this unit time conversion factor, which I just showed you, to the power of 3. Why is that? Because a mass is volt-ampere second to the power of 3 over square meters. So we have the second to the power of 3 in this equation of a mass. And we have hence to take the iSpace base-time artifact factor and compensate for the wrong time by the power of 3. And that's it. And then you get the right mass.
Okay.
In electron volt or in kilogram in the books, like up to the 12th digit as you wish. That's simple.
Okay, right.
Now choose, is that accidental or is it just good theory?
Yeah. Right. For that thought, can we take about 15 minutes, 10-15 minutes break now?
Okay. Yeah, that sounds reasonable.
Thank you.
And Christopher, I want to ask you, if I switch off the live now, I can put it on again, right? Or
I don't know how that works.
Yeah, I don't want. Okay, we won't try it now.
If you want to, we'll experiment with that later. Okay.
Yeah, thank you.
15 minutes.
Okay.
Hello, Beck.
Hey, how's it going?
I wrote you in the private chat some comment on how to best massage the 1/6961 quantum of time into your understanding, to put it this way.
Okay.
We could do that in a one-on-one, if you prefer that, for high-end technical questions offline. Or if you're there, we can do that live right now. Just it's the same presentation I gave in the first meeting. Essentially, we had not enough time. We were flying 5 minutes over that paper, essentially, in the original presentation of mine. We have seen it. It's just the standard paper on ResearchGate.
Yeah, no, yeah, I think I understand that. Like, I think what I'd be interested in is, I don't know, it's hard to sort of put into words, but so you have these equations and they obviously work, they give these very accurate answers. And then it just seems like you have two parts to your research. There's the sort of the geometric background justification, if you will, and then you have all these equations. And I think there may be, like, the equations are well developed. The other side seems to be a little bit less developed somehow. And the
theoretical part of iSpace theory is not developed at all. I gave recently an answer in one of the forums that iSpace theory doesn't imply nor try to impose any specific geometrical model of space-time. It just is first-hand order multiplicative, in my humble opinion, correct result of what constants of nature really are comprised of.
Yeah.
But when you accept constants of nature are comprised of small geometric integer numbers and geometry like pi and golden ratio in some dimension, like to the power of 1, 2, 3, 4, 5, 10, whatever is necessary geometrically for these constituents, then there is not much left to go to the next step and say, what does the exponents you see in your equation mean? And when all the exponents of the, say, electron mass would show you to the power of 3, I would say, oh, yeah, then likely it's three-dimensional, the electron, isn't it? Yeah.
Yeah.
Yeah, but I see alpha to the power of 10, and that is not coincidental. So it's likely 10-dimensional.
Okay.
From the basic structure. Yeah.
Yes. So yeah. So
and that's where we're going into the field of string theory, where I am not at all endorsing string theory, nor rejecting or commenting even string theory. I'm just saying string theory came up with a 10-dimension. It wasn't me. Yeah.
Yeah. So I mean, you could have something to the power of 15 or 18 in your equations, could you? And then
it depends on what you try to answer. When you look individually at the mass factors, then the mass can be, for example, split into smaller numbers. And if that smaller numbers would be arbitrary things like prime numbers, then they would be completely meaningless, because they would be human artifacts, which I don't understand then, but they can be split in multiples of 10 plus 1, and that is not a coincidence ever. Because the 10 is the most simple scaling number you can do in the universe where you stay in the decadic system. Now you could argue a higher entity will not have 10 fingers, and a higher entity will surely have not used decadic factors to make G exactly 10 to the power of 48 bigger than some Planck constant. And my answer on this is no, it wouldn't. But it will make it consistent by some multiplication factor.
What does that mean, Cardic factors?
Look, when I was 15 years younger, I found that the iSpace basetime could be explained by assuming a 10 to the power of 4 zero numbers. And I, at the time, called that I-flat, meaning that if you take any physical constant and have a flatness, inflation-like scaling factor, which is decadic, then you could calculate something extremely small and make something very big out of that, giving the measurement values we have in the lab. Because the measurement values in the lab are ohm. Ohm is volt over ampere. And what you would expect for a quantum effect is femto-ohm over femto-ampere or something like that, really small.
Yeah.
But what hits your face is volt over ampere, is golden ratio ampere over 6961 volt, which is human size. This gives the quantum Hall effect. This is in the lab. You can go in the resistor of my lab and find a resistor with 25 kilo ohm. That is not quantum small. It is human size, big. And the interesting question is, why would that be? And I was naively thinking at the time that some magic makes the very small linear bigger, that we can measure it in the lab very precise, up to 12, 20, or however good your measurement equipment is from a clock point of view. And we only see the quantum effect in some few selective experiments, like the quantum Hall experiments and the Josephson experiments with the squids and so on. There you see them. Suddenly you have quantized voltage, extremely precise. They have quantized resistance, extremely precise. And when you combine them, you have a charge, very precise. And charge is undoubtedly structured by electrons. And electrons are discrete the last time I looked. There is no half electron, no quarter electron. And I'm not talking about quantized Hall effect like a fractional quantum Hall effect here. These are geometric effects. This doesn't mean that the electron is a third electron and waiting for its other 2/3 parts to recombine. Yeah? That is all geometric nonsense. Electron is atomic minimum you have. Either you have one or you're not. And you can have the electron destruct, and then you have the energy of the electron, this 1.02 mega electron volt, I believe to remember if I'm right, which when an electron or positron destructs, you have 2 photons of that energy going away in opposite directions in your experiment. And these photons are, once again, in the detectors, easy to detect and extremely precise with the energy of a single photon, a single electron and a single proton dissecting into these energies. The more interesting part is the reverse experiment, where you have a precise energy of photons of that energy and shoot them onto centralized points or some catalytic atoms which are waiting there in your traps, atom traps, and then suddenly a electron-positron pair appears out of nothing. That means the experiment proves that the effect is reversible, so that you can destruct something which is like as big as the Eiffel Tower, and you get the parts of the Eiffel Tower on the floor when you explode it. That is one thing, is easy to understand, but that you throw the parts of the Eiffel Tower with a certain speed into the direction where it should construct itself, and then suddenly it makes boom and an Eiffel Tower appears in front of your eyes, is really dubious, isn't it? Yeah? How does the universe do that?
So baryon asymmetry, how does the asymmetry comes? That
this we don't know. So I can only say it's easy to destruct something. When I have a model for an electron, and the iSpace definitely has a structural model for an electron in the sense of the constituent multiplicative parts of it could be independent. Maybe not, but if they are, they could be independent and could dissect. And if they dissect, each of the individual parts represents some energy, because the electron in its full blown constructive form at rest would have a rest energy, and that is exact in iSpace. The energy which you gain when you move an electron has nothing to do with the iSpace theory. So this is the big question. When you move the electron and you accelerate it in a magnetic field, where does the electron store the additional electromagnetic energy, which represents a form of mass? And here the iSpace theory comes in and said, as I can calculate G from the electron and the mu zero and the fine structure constant, I can assume or deduce that the gravitational energy we have is in fact not gravitational, but also electromagnetic. And hence the electromagnetic field around a rest mass of an electron gets bigger. The energy in the electromagnetic field around the electron is the mass which you measure, is the inertia which you feel when you try to accelerate something and overcome its inertia, is all electromagnetic. But that would in turn mean in what medium? Where is the water where the fish tries to swim faster than the water flows and gets an inertial resistance, bypassing the molecules in front of them and collapsing the molecules behind him? Because that is what a fish is doing. He's swimming in HO2 molecules. That is water. Water is discrete. Water is quantized. There is no fluid. This is just in your brain when you drink water because you're thirsty. Water is HO2, the last time I looked. And that is very
H2O. H2O, yes.
Sorry, yeah.
It's okay. Yes. Hope I didn't miss much.
You get the idea. So water is quantized.
Well, hey, Rajan, if you check the chat, Christian put in some information there explaining more details surrounding how the quantum of time and, well, I was interested in the geometry of the theory and then the calculations, and just maybe that it'd be nice if there was, you know, more of a bridge between them or something. But I think listening to you talk, there is, you know, you have that already. But I think, you know, maybe if you were to publish, you know, the way you publish a lot of Mathematica equations, but if there was more discussion, I don't know, fleshed it out a bit, or
I know exactly what you mean. So I would have to publish a peer-reviewed paper with all the prosa, what the hell all these numbers mean one by one, how they assemble together, and all that is only in my mind. And that has to do with it's just my hobby. I'm doing only all of that research in hobby mode, and I'm happy if I find out something new. I have to immediately grasp it and follow it up, or it's gone.
Yeah.
And most of the time, I only have the time to follow it up in Mathematica documents. And as it's really, really interesting, I try to publish them in a way which is a less work for me and a minimum work for you to jump into and read. When I give you prosa, then the best to do is really watch my video. I have people who seriously criticize iSpace theory for not even possible. I say, but it is possible. I did it.
Yeah.
Just read it. So I give them the link to the TEGS video, which I made, and said, have the look from time minute so-and-so to time minute so-and-so. It will be 1 hour of your time, and you completely understand it because it was step by step from scratch explained. Everything is completely logical and easy to understand, and is better than any paper you might ever read. And they come back, I don't have a time for 1 hour to watch a video. And I said, okay. So if you don't have a time to watch a video, you also have not 1 hour to read the paper, which I need to write, which means takes me a week to write it properly, or 2 weeks. And you will then later say, when I do write the paper, I have no time to read that either.
Yeah, exactly. So it's efficiency really that you're going for. Yeah, I follow that. That makes sense.
The math stands on its own. And the math is like source code. Would you be a programmer, you would immediately understand what I'm doing there. I give you source code with inline comments, and the inline comments are the paper, and that's it.
Yeah. Well, I understand programming, so there's, But I'm also
especially the older ones don't.
To read, you know, prose and with images that like sort of evoke what you're saying more. You know, so just
have you read my paper from 2015 from IMS, because that is prosa?
Oh no, I haven't. What's it called? What's the title?
See? So this is what I mean. You need to take the time to do the things sequentially. For me, this is 15-year-old stuff, so the 15-year-old stuff is not even active in my mind.
Is, or else I can't read it. Because I've looked through your work, but a lot of it is just equations. So
I give you the link. Wait a moment. Okay. I have to just open the other browser.
See, you said there's something to chat. Only chat I'm seeing is what Christian said. You know,
that is it.
I'm back. That's it. Backstage. Yeah. That's it. That's all.
Oh no. There's Oh, maybe he sent one to me, so maybe it might only be to me. That's fair enough.
Send in the private chat. I'm not sure who reaches this, depending on
okay.
who's
Well, I can
call.
repost it to Rajan then, yeah.
Okay, thanks. Oh yeah.
Give me a second, then I'll post that to you.
Prove physical existence of 1961 as quantum of time would be.
What I'm really lacking, guys, is I had a project, and that project was explaining it over the years. It was like a blog, and for some reason I really don't understand, ResearchGate killed the project log.
Oh, okay? Really?
Yeah, and all that information in the project log where I could easily post and say, hey, read that sequentially as long as you like. The simple things start first and the more complex and the references come in. It was about 20 pages of project log, like a blog. And I have fortunately saved all that. So is it probably a good idea when I do the project log in a, say, updated form and post it as a PDF of a summary what I posted in the past as an introductory paper and put that in position 1 in my ResearchGate profile? Would that help?
That would help. That would be good. Yeah, I'd like to see something like that. It would just something that would be more useful.
A summary introduction or something like that. Yeah.
That'd be cool. Because
I still have it. So this is okay.
Rajan was talking about that they killed projects on ResearchGate.
That was really a technical reason. I do not understand why they gave never a replacement.
Yeah.
So old projects don't stay up. It's just that
they killed the project section. The whole web section of projects disappeared, including deleting all your data.
Bizarre.
No idea why they did that.
What would you say, Raja, or no, sorry, Christian, as an IT expert person? Like, let's say I upload I don't know, what is it? Usually 8 megabytes for a PDF or whatever it is. 15 megabytes or something. And then I upload that and then I change it. So I upload another one and another one. Like, are their servers just overloaded with PDFs, do you think? Or can they handle it on ResearchGate, I mean? Or do you think that they're...
No, you can handle it. I think ResearchGate will not delete any of your papers. You have version papers even there. So it's a good thing to, from an IT-centric point. It was a rare exception that they deleted the project.
Whether they would delete the papers, but I suppose really what I'm asking is, do you think they killed projects because they have an issue that there's just too much data?
They had technical issues with that, yeah. But I've never asked informal reason why they did that. Many people were upset, and they said not many people were using the project feature. That may be true. And the few who did use it in block style. And probably this block style wasn't compatible with their advertisement needs, or it was doing technical harm due to that way. When you block there, you had special problems with the special characters, with the umlauts and so on. That is true. So some software they used in the blocks historically were probably not good JavaScript, or I don't know what happened there in detail.
Okay, Christian, thanks for the link, but I'm looking at it here. I can see the abstract. I go down to read the paper. It says a preview of this PDF is not available. So should I download it?
The paper is always available when you can live view it in the ResearchGate link, or you download it as a PDF. The abstract just says download it because when you view it in the web page, it will reduce the images in there to a size which might not make the equations good readable.
Well, maybe I'm using the wrong browser. I'll try a different browser. There it is. Loading the PDF. Yes. iSpace driving G from Alpha E. Okay. Yeah.
It's a very prosa document driving you from the arguments of the geometry to really everything. And the attachment of that, is that what you probably know? The attachment to this document is the one where I published the exact form of constants of nature already 15 years ago. They haven't changed since today, but the arguments of their constituents have changed. Like in the paper attachment is there's a magic prime number 6961, use it or you don't get the right answers for constants, but I don't know what it is. And today I would say 1/6961 is the quantum of time, has a unit of seconds or iSpace seconds, and would be differently explained, but the value still wouldn't change. How many theories you have seen who published something over 15 years and didn't change a single bit of information?
Christian, you're roboting like mad there. There's something wrong with your connection. You're kind of roboting and.
Is it better now?
It's like you're jumping ahead of time.
Is the voice better now without the
video? Yeah, it seems better, yeah.
Okay, maybe someone in the house here is a VG has started streaming some videos in the evening, so
taking the bandwidth. Oh, yeah. Do you ever watch Red Dwarf? Do you know the British comedy series Red Dwarf? Either?
No, I have much more things to do. I'm working in a television company at Sky, you know. So at the moment, I watch so much television at day jobs that I have really not so much time to.
Not that much difference. You can put the video back on. But one of the things is that we talk about information, right? I was just thinking there may be 4 types of information. That's why there's these different times. The information, one of the things I said, the information that comes to me, the form of gravity, information that goes out from photon. But there are 2 other information. One is the sound, the other one is a superluminal. So there could be 4 types of.
It's interesting. I'm not sure on that front. I mean, could information? When I think of information in information theory, I think of like some very abstract concept that's not necessarily.
Then all of them come together in the center, you know. So that forms. You can call that's the super information or the information. The other ones, like information that goes from me, maybe like time. And the information that comes from the other one is the actual information. So the information then is the center thing, the pool thing is the information. And then you have these 4 different types, which can be called the sub information or whatever you can call that, you know, the subspace or whatever, you know, you have to invent something. But gravitonic information, photonic information, then you have the what you call the sound or the vibrational information, and also the superluminal information. So that way, I think, you know, I think if you look at that, I think we'll and also the fact that the time is linear only within that time, and the time becomes non-linear in the astrophysics or the general. Then
well, I'm going to ask about that, Rajan, there, because that's interesting. We live on. We are above the quantum realm, like the Schrodinger length. So then wouldn't time be non-linear for us?
Yeah, actually it will be, we are in the interface between the linear. There is inside us, there is linear, but outside us is the non-linear. So we do face both of them.
Well, when you say outside, like, do you mean?
Outside our body, you know, kind of outside our body.
So is that like our body, our minds or something, convert the non-linear time into linear time or something?
Yeah. So suppose I'm just talking about myself. I'm thinking about myself. I may be in the linear. And then I'm talking to you. I'm communicating with you. That's non-linear time. That's non-linear time.
Why do you say that?
Because my thought process at that time stops, and then I'm thinking. So we are trying to correlate that. So it's an interface. So you are at your own linear time. I am in my own linear time. But when we communicate, we are in the non-linear time. So we have to pass through that stage. So we switch off our linear time, kind of. I switch off my thoughts. Otherwise, I cannot communicate with you. So I don't know whether you feel that way. In the sense that I cannot.
Interesting, but when you switch off your thoughts to speak, I mean, don't you feel that is still linear?
Yeah, actually, we are in the interface. We are actually linear. So suppose we have like a Venn diagram. We are linear and non-linear and linear. We are in the middle of that when we communicate. We are
okay. Well, I mean, I can see that. I mean, you know, when you're walking around your house or something, drinking a cup of coffee, and you're thinking about things that have happened in the past and future. So, I mean, I think there's a non-linear aspect to us, isn't there?
Yeah. So in that,
that's pretty interesting, Rajan. I like that. I like that idea.
Thank you.
And I was also thinking about some of your previous work that you did with the, was it S6 symmetry group? And how you were talking about, you had that matrix where sometimes there's a particle, sometimes there isn't a particle. And that's actually, you know, when you were talking about the Lagrangian in my model, that the new unique hyperspheric model, it's the first time I said that actually, I think, but is the, you know, you have the ray that comes down and hits the hypersphere and then goes on to project onto the tangent plane. And if there's nothing there on the sphere, it projects nothing, like space. But I was suggesting that it's projecting all the particles at the same time, which appears to be nothing in a sense, or the, you know, 0 point energy, if you will. But then if it hits an electron, whatever it's hitting is like everything but an, but an electron, and then it projects the electron. Now that might not be true, but you know, because there's other ways of looking at it. But that was just a kind of an idea I had. But I liked, you know, let's say it is actually hitting an electron and just projecting the electron down. That could also work. So, but it reminded me of your work where it's like talking about particle, another particle, and then no particle. I thought that was interesting. So that might help you a bit with your work. Also, if you look at my new paper, when you get the time, it's called Turning the Universe Inside Out. And in that, I have a 4-dimensional hypersphere. And so the rays of light are coming down and projecting into 3-dimensional space. So it projects all of the universe in 3D space. So the point I was making there is, so like if you were to select any object in space, let's say a galaxy or a star, and it has a particular coordinate value in the SDSS catalog. So let's say that's right ascension, declination, and Z redshift value. Then those are the 3 dimensions of normal space. But the because we have the hypersphere as well, that's an extra 4 dimensions. So that's what, 7 in total. And then you have the point at infinity where things are being, well, it's not actually infinity, it's 0, 0, 0, 0, I think, or maybe 0. Oh no, sorry, 0, 0, 0, 0, 1. How many zeros is that? 3 zeros and a 1 at the end, because it's 4-dimensional, right? So sorry, I lose tracking on this stuff. So that point at infinity, let's call it, or the projective point, is like the 8th point in the so there's technically 8 dimensional. So any point in the universe that we talk about can have 8 dimensions associated with it. One of those dimensions is the identity, in a sense. It's common for all points in the universe. So that means that technically we can describe any point in the universe using 7 dimensions. But then we have to ask, well, where is this information being projected from? You know? So the source, well, one thing about the source is we can point in any direction in space, like whatsoever. And the source is, if we exist in the tangent space, that is, which we do, the source is in any direction you point at an infinite distance. So that's where it is. But it is also in one location if we were to point towards 0, 0, 0, 1 in the 4th dimension, which we obviously can't do. So, but it is in one place. But so all the light that's streaming out of there could in fact be coming in from another location, which could be a second hypersphere with a second tangent space, which would make the model 15-dimensional in total, which is interesting. It's an interesting number, and it has a lot of, you know, it has a lot of relationships to I think super elliptic curves and all sorts of things. So prime numbers as well. Obviously special relativity in some cases, quaternions, just loads of stuff. So yeah, it could be interesting. But on the point, there was another issue I was going to say. Oh yeah, so let's say we take let's say we take just the two-dimensional version. So we have a two-dimensional tangent plane and a unit sphere we're projecting. So we have 2 dimensions on the tangent sphere, tangent plane, and 3 on the sphere plus 1. So that's 6 in total, right? Yes. So 1 being the identity. And then you could play around with the symmetry groups, you know, so by permuting the 4, let's say the 5 real dimensions and leaving the identity, you just permute those and see what patterns it makes on the tangent space. That could be a fun little project as well. Then moving up to the 3-dimensional model, we would have the identity plus 7 permuted values. And if we were to do that, I think, forgotten the exact numbers now, but anyway, there's a relationship between that and I think it's called the snub-nosed 24-cell tesseract, something like that. Anyway, but it's a subset of the 600 cell. When you take out the 24 cell, what you have left is, I think it's called a snub-nosed 24 cell or something, but it has 96 vertices, and you can build them up by using these identity elements and then permutations of these 7 other elements. So it's a long shot, but there could be some fun geometries and stuff. You know, you could take a star and then permute its dimensions, in a sense, if you like, coordinate values, and see where it ends up on the sphere, and do that with lots of other ones. And
Christopher, may I ask a complex question to be answered in a simple form for a non-expert of Mars like me? Why do so many experts in cosmology respect to string theory believe that octonions have anything to do with reality? The 600 cell and the 24 cell and all that I read in even 25 years ago already in some papers, and they made beautiful geometric images which were prominently displayed even in some physical, scientific, honorable things, but they never come up with a good argument why that would be anything related to, say, calculate a single constants of nature out of the octonion as an example, why that would be a good idea. They never come up with anything except nice geometry in N cells. And I'm not saying that is the wrong direction. I'm just saying, think you would invent a mathematical superpower geometry, then naturally anything would be included into that geometry. So you would be tempted to say, yes, with that geometry, I can explain everything, and maybe you can. But it is super determined in a sense that it is so complex that it includes by nature everything. And hence, of course, if you know what to select off, which is real, you find suddenly an electron charge or an electron mass in it. Could be. I'm not saying, I have not found anything where that happened, actually, but if so, would be a great achievement in its own. Nevertheless, the theory that should tell you what branch in its octonion or whatever related geometric entity is physical and what is just, well, by work, which says it gives a number but is unphysical. And then you would need another theory to say which is the unphysical one and which is the physical one. It all boils down to a paper, and I have a book about string theory to disclose. I read, not understanding it, but I at least read it. Okay.
Yeah.
And in it's about 500 pages, is said in string theory we have so and so many dimensions because of this and this mathematical assumption. I said, okay, fair. Yeah. One is 10 dimension. Sometimes it was 26 dimension. Some other is 11 dimension, like the M theory, and so on. You might know. And they come up with a degree of freedom of 10 to the power of 500 entropy-wise. This is an extreme number. Even for iSpace size is an extreme number. 10 to the power of 5 different possible universes is a little bit much. And their explanation was, we need to just find in these 10 to the power of 500s the one we are in. I said, okay, that sounds easy, isn't it? So when you have a theory where it has such a big possibilities, of course the right one could be in the set of possible variations of the theory, but it's not really effective, isn't it? It's like I give you the equations of iSpace without telling you in what geometry in detail you need to combine them to say, look, when you take a golden ratio and a pi and a 6961 and combine it in the right way, you will find electron charge, electron mass. I said, yeah, do it yourself or what?
Well, just to interrupt there, so, or just to add something to that, what I think what I was getting at there was I was looking at some of Rajan's work and suggesting, you know, there's a similarity or there with the rays, you know, hitting something is a particle, something isn't a particle, and these things are still something, you know, there's still a sphere there and there's still a tangent space. And then, of course, the S6 or S7 permutations was also kind of related to work Rajan was doing. So, you know, we can find these two things are both in the UHM model, the unique hyperspheric model. So you know, it's an area of research. But if we look at this paper, I don't know if you can see this.
Yeah.
Wait a second. Right. If I exit this and look.
Is it the new one? Christopher,
no,
is the new one?
No, it isn't. Although I can show that. But right. So you know all this stuff about U1, SU2, SU3. So SU3 is what quantum chromodynamics. SU2 is more like the weak force, but it's also to do with fermions and spin and all of this. So they've been looking at these different groups, group theory and group symmetries and all of this for ages, and hoping that there'd be some link between that and the Lorentz group to sort of combine quantum physics and general relativity together. It's a process known as representation theory. So I was initially working with quaternions and I was getting some interesting geometric results. And from that, I discovered, and using, was it octonions as well? Well, certainly quaternions. Anyway, I came up with this concept of 48 modified standard model particles, which I actually called DGO originally. But all of that's kind of fallen by the wayside, because when I discovered these 48 particles, which are really just like the what is it, 32 known particles plus 4 Higgses and 8 gravitons. So I noticed that, you know, that's 48 is 2 times 24, which is the 24 cell. And I was initially really resistant to the idea of using the 24 cell. But when I saw this and the fact that that's related to SL2C, and then the binary octahedral group is just the double cover of SL2C, also known as GL23. It's the double cover of the 24 cell as well. So I started diving into this because we could imagine that the 48 particles of this DGO were related to the matrices of GL23, or which is the binary octahedral group. So then I realized that, so there was a lot of stuff there, you know, the SU2 was already in there, and I was able to create SU3 as well with a different method that's not in this paper. I had a model of electroweak isomorphisms, exactly, within the 24 cell. That can be seen here. I think a cycle notation. S8 is obviously related to 24 cell and the binary octahedral group.
I'm not saying I do fully understand the geometry of this 600 cell or something of the other, not even the 24 cell maybe. But what I do understand is that there are symmetry groups, as you said, in the sense of SU2, SU1, SU2, SU3.
Yes.
And all the physics so far, which is mainstream, is based on these 3 groups. And other people, very clever ones, have tried to find supersymmetric particles like that and failed miserably so far in the experiments in the accelerator. Nothing came out of that. It's a 25-year research program with 0 result.
I know, yeah. It's very true, very true.
And that means that the supersymmetry per se was one of the attempts to take the multiplication of something with another row, column in a matrix, and make the matrix bigger and find new particles, but there were none. Now,
yeah, it doesn't work, and yeah, that is a problem, all right. Or maybe this is the wrong paper. Oh yeah, it is. Sorry about that. But so this was the right paper for what I was talking about with the gluons, because we have like 8 gluons, which are here, different cubes within the tesseract. So there they are. The color of these cubes are related to the 8 gluons. So, but then I realized a better structure would be in the 24 cell would be, well, the thing about the 24 cell is it is created out of 3 16 cells. So, and in the center of, we can see one of the 16 cells. I've just, well, actually, so if you see the purple triangles here, they create a tesseract, and in the center is a 16 cell. So we can take the colors and gluons from here and just put them in here, and it works the exact same. Then we can permute, not using SU3, but rather, what is it, OR3 or OR4, yeah, the rotation groups of 4 dimensions. And we can do like basic QCD with that. So that's pretty cool.
May I ask if whole of QCD could be wrong in a sense that if we only have electron and positron and dynamic arrangements in a box of electron and positron will give neutron and proton and all the other masses of the atom one way or another, then this kind of geometry could be a hint for abstract masses like gluons, but gluons in its own would not exist, because they're only electrons and positrons in dynamic movement. Then wouldn't it be a better way to search for hyperstructures of electrons and positrons in a multidimensional space? So the approach would be the right direction, but I don't believe in quarks anymore.
Oh, okay. Well, that's fair enough. I mean, like, I suppose you're entitled to that. I think I was just working within the standard model. I didn't want to, like, you know, I was just trying to work within what had been already discovered, learn about it, and trying to apply.
I know everybody is doing that, but when you think on the precision with a positive charge and a negative charge in a proton compensates the electron charge, that is frightening. The last measurement I have read was 10 to the power of 21 precision. So this is near iSpace precision, by the way.
Yeah, is
so
this
they did so much experiments on that they have a confidence level of 10 to the power of 21 exactness of positive and negative charge.
Yeah, well, there is this theory that the proton is made up of an electron and a, I don't know.
That leads to that in the end, because when you have such an exactness, it is clear that some electron is sitting somewhere, because only the electron will have the charge of the electron, right? You don't need a proton with the same charge. It is an electron with opposite charge, and that would be just geometry, like your cubes or whatever. You inverse the direction.
Yeah. Well, I suppose like this was, you know, what I was beginning with. So I have the gluons, and then I have 8 gravitons. So they're all like neatly arranged in this sort of interleaved order, and then you can rotate this cube and then get gravitons with bosons or gluons with bosons, depending on which way you rotate. And that was really it. And then I worked out some masses.
Can you really calculate the masses and the charges of individual gluons and gravitons from this model?
Well, this is what I attempted. So actually, this would be interesting to run this by you guys, and you can, I mean, I won't go too much in depth. So what I was looking at was, if we imagine these lines within the tesseract as being sort of, how do you say, Feynman decay paths, following those lines was like we had so since we have 8 gravitons, I basically just take the nomenclature here, or the, you know what I mean, the stuff anyway, how do you say that word? It's not nomenclature. It's
yeah, sort of.
It's label. It's like a label.
Yeah, like notation. We take the notation here, but we replace gluon with capital G. Okay, but it's the same thing overall, except with gravitons. So here we have a G4. So that's one of those, and then we have the weak boson W plus, and then we have 2 Higgs bosons here, and some gluons. And so we can look at different decays. So if we have a Higgs boson that decays into a G4 and a G6, that means we just half the energy of the original Higgs. So that's this value, much like what Manuel was doing before. So that gives us a value. We can convert that to joules, and then we can change that into hertz for the gravitons. So that's hertz value for the graviton according to this. However,
how does it match with 10 power 19 that Christine is saying? Does it match?
Oh, well, yeah, actually, that's interesting because I wasn't entirely sure what Christian was getting at. I mean, you look at the gravitational constant is this values 10 to the minus 11, but you're obviously talking about something else. Not the gravitational constant, but the gravitational
field. The speed.
I can calculate both of that. So they are all related, okay? And they are all related by exact relations.
Right. So you're talking about 10
or
to
anything.
the power of 19, which is a huge.
Yeah, the electron charge is. Let me do that right. And I have a Mathematica here that I don't give a wrong answer. But the electron charge numerically is 1.6021764 to the power of minus 19 ampere second. Yeah? And when you divide that number by golden ratio, and you divide it by golden ratio ampere, then you get 9.901995244 and so on, 10 to the power of minus 20 second. And that is the iSpace baseline. But this is the human part of it with the human artifact in it.
And that's the gravitational.
Take that number and divide the ITBHA out, then you get 1/6961 second, which means that the ITBHN is a factor of, and this could be interesting, 689277889 exact, because it is an artifact, so there was no more input precision. I cannot give you more output precision. It's an artifact, but it has an exponent to the power of minus 16. So when I make an integer out of that, then it would be the integer 689277899, just like the speed of light is an integer, human defined exact. And you get an exponent of minus 16, 14, 15, 13, 12, 11, 10, 8, 9. It's about the speed of light. It could be coincidental, it could be not. But all of that is related, and whatever you do there, you make frequency calculations. So the frequency calculations are not relativistic.
Right. That's what
when you believe in a relativistic universe, you need to accept that the relativity bends time, and a lot of the discussions in ResearchGate are about exactly that topic. How can you know that your frequencies you measure in redshift and all that are the ones you want to see, and not physically deviating? When a star explodes, it gives a precise, because the explosion happens always at the same Chandrasekhar limit. So it is exact in the sense, the mass is exact to the last atom when it does a boom. And after that boom, you put light.
I think we're getting away from the topic a little bit, though. I would like to steer back just to what we were talking about here. Like we have a frequency thing that's e to the 16 hertz, and that just comes out of, you know, this equation is used.
Yeah, but this is an energy calculation. Out of an energy can be always in different units given as a frequency or given as a mass or given whatever you want.
Well, we start with the mass and then I just go to the frequency.
The conversion is exact. That is what I want to remind you. The conversion is exact, even in a SI unit system. C squared is an exact number. So when you convert with the speed of light squared, you get
show you something here, and then I just want to get your opinion on this, because I wasn't entirely sure about whether what I did here was correct or a good idea, but I think it's, I don't know either way. So
give me your value for the joule here, for example, to make it into proposition 9.9976. Is that I'm reading right?
Where's the, yes, this is for joule.
9.996. Let me type that in Mathematica. 9.9967. No, 9.997.
9.9976, and then followed by a load of zeros.
To the power of minus 18.
That's
joules.
right. Yes.
And that is something which can be exact in iSpace. I want to just now see in what relation to other iSpace values that is. Give me a moment and I calculate that.
Okay.
Joule is volt ampere second. So the value 99776 to the power of minus 18 is exactly the same when I make an integer out of that and change the exponent. Agree?
Okay.
You have just zeros behind there because you cannot calculate it with more precision because probably you have a g as an input value or something. So in the end, you can say this is the same as 999776 to the power of minus 12.
Why are you putting an extra 7 in there?
Sorry?
7. It's just 1 7. 99976. Yeah.
But the e is a 10 to the power of exponent, right? Small e here is just convention. Normally, you don't see the e function there. This is really meant to be a 10 up to the power, right?
Yes, exactly. Yeah.
Okay, that is important, of course. Yeah, but 10 to the power of minus 18.
Yeah.
When I divide it by ITB, this is a factor of 100 away about. Yeah.
Okay.
From the frequency. If that is an SI system calculation, because you say second there, so it's an SI calculation from my point of view.
Indeed.
Volt is 1 and ampere is golden ratio. So even if I take golden ratio into account and multiply with golden ratio, so it's a maximum of 163 away. So it's in the range of alpha away, about 137 something. Yeah.
Alpha
so
away.
You can always be tempted to say it's related to something or not, but
yes.
What volt did you multiply into that joule? What ampere did you multiply in that joule? And what seconds did you multiply into that joule? In other words, how did you get to the number?
Well, the joule, yeah, that's a good question. Oh, you divide, I think, do you divide by the Planck length or no, the electron volt? Hang on a sec.
You start in electron volt. This is nice, but electron volt is not electron volt, but electron volt over c squared. You're not allowed to change the unit system by setting c to 1. You need to really do that and not leave it away. Most people in all papers leave the c squared electron volt away and just write electron volt, but there is no electron volt. It's just a mass is electron volt over c squared.
Yeah, I think you could, yeah.
In certain unit systems, this is the same because the c is defined to 1 in that unit system.
Right.
You must not leave it away.
You basically you get the mass, right? The graviton in this instance is decaying into 2 Higgs particles. Yeah. So each one has 124 GeV. All right. No, sorry. The Higgs particle is decaying into 2 gravitons, which therefore splits down to 62 roughly. GeV.
Giga
so
electron volt?
Yeah.
So it's 64 giga electron volt per c squared.
Right, yes, exactly. Then you multiply that figure by 1.6 times 10 to the minus 19 to get the joules.
Yeah.
So, yeah. And then you have to do another
That is electron volt to kilogram conversion. That is exact in iSpace. So
yeah, and then you have to do another equation to get the Hertz value, which is to divide by
c. That is trivial. Yeah, and you put the length out, and you have the space the second. So
well, no, you divide by 6.63.
Yeah, the Planck constant, of course. Yeah.
Oh right. Okay. So then my intuition here was that's the equation for a photon, which is spin 1, but because we're dealing with gravitons here and they're spin 2 massless particles. I just like my intuition must have multiplied by 2 because spin 1 spins once, spin 2 spins twice as many times, so its Hertz would be twice the amount. That's probably not right, but that's, I mean, what do you guys think? So that's the end value there is 3.015862726 10 to the power of 16 Hertz.
But it's spinning in the dimension, it's spinning is different, right? It's spinning in the planar direction or it's in the solid direction? The graviton is in the solid, like 4-dimensional space or 3-dimensional space.
Oh, I see what you mean. Well, these points are like pretty much dimensionless in a sense. I mean, the space is 4-dimensional. I have other stuff with I think string theory just has it as like it's a loop, you know, around a torus kind of thing, closed loop.
So there will be a correction. What I'm saying is there will be a correction factor. It may not be 2 exactly.
Oh, okay. Yes. All right. Interesting.
Yeah.
That is an interesting point, Rajan. Thanks for that.
Oh,
so
sure.
so yeah. No. That is very interesting. Subtracting this. So so basically all I found was that the ranges are in the soft X-ray range. Sources of this kind of radiation in the universe are pretty much everywhere: galaxy clusters, remnants of supernovae, neutron stars, and stars including our own sun. So that was it for that. I was on the wrong paper there though, so I meant to show they have very similar titles and they're right next to each other. So there's this one, which is how to basically, what you do is you take the 24 cell for the gluons and gravitons, I think, is well defined, but and for the particles, the fermions, but in order to know which fermion particles map to which bosons, you have to do some special rotation. But it turns out there's actually 12 ways to do the rotation. So there's 12 separate configurations of particles. You can see that in Appendix 2, which is down here. Not that one. Appendix 3. But this isn't all 12. It's just a certain number of them. You see, like, here's the bosons, and then this is a list of possible fermions that you'd have with this. And the fermions are divided into matter, antimatter, left-hand, right-handed particles. We don't have spin up and spin down in this system because there isn't enough vertices in the 24 cell to accommodate that. So that's why we moved to the 600 cell, and that's why we need the S5 symmetry group to do that. And then when we do that, we wind up with, well, there's a couple of other things we have to do that also involves the number 15, which is just happenstance. Oh yeah, there we go. So this process recovers S4 for all 4 groups of the 96 matrices. So these 96 are vertices within the 600 cell. And so then we can add in the spin up and spin down characteristics, which is a sequence of 0 for the bosons, then 1, 1, that's the first. So essentially, just to break it down here, there's 5 24 cells within the 600 cell. So the first one's devoted to the bosons that we saw earlier. Then we have, then the other 4 are, 2 of them are devoted to fermions and 2 to the quark fermions. Sorry, so the charged leptons and the leptons and the quarks. So 2 are devoted to, let's say this one is lepton, this is quark, and this is quark. So then now we have spin up and spin down for all the particles. And then we can also add in color charge by doing, what do you call it? Color permutations. And so this is the 600 cell with all of the particles of the standard model. And then we only need to permute the color charges using SU3. And then we get, all the color charges as well. So that is all the particles of the standard, or this modified version of the standard model with
Gell-Mann. You use a Gell-Mann matrix, like Gell-Mann.
Yeah. To permute these, you just apply the Gell-Mann matrix, exactly. But I don't know if these colors are exactly correct, but they're close enough. I mean, for the 24 cell, they are exact. So here they are. So SU3, these are your quarks, and these are your leptons, and there's the color permutations. You see the way it switches. So this is one 24 cell in this column, and another one with a permutation here, and the last permutation there. So you just do the same thing for the 600 cell, and that's what you get. So we've looked at that table, and the end results are, these are the particles running down here. So there's all the bosons, and these are the coordinates for the 24 cell embedded at the center of the 600 cell. There's the spin, and there's the color charge. And we keep going down, and then we move into the charged leptons with the spins. And we notice that in the coordinate value, there's always like 1/2, which could indicate a fermion, which is spin 1/2, and it's always positive when spin is positive, and always negative when the spin is negative. So there you see. And then we also have the golden ratio, or this value here, which is either golden mean. I think it's the golden mean. And so that was kind of the idea, but really, ultimately, this has been a project that, you know, I'm passionate about 4-dimensional geometry, and this kind of.
How is that coming along, the data modeling? I think you know, we discussed about your project, but I think, are you continuing now?
Well, this was kind of the culmination of like a couple of years work, but I think I just got the idea maybe late. So it took me like 4 or 5 months or more to actually get around to do this. But this was kind of it. I was then going to go on and embed this into the 24 cell, and then, sorry, into the 120 cell, and then expand that into hyperbolic space, so that it would see if I could find a connection between that and maybe special relativity. But that was pointless, because I think special relativity and quantum mechanics are well connected anyway through things like the Klein-Gordon equation. But then you could also shrink it down further into the Borromean rings, and then you'd have all the particles would just all mash together into these 3 rings, which would be interesting. You know, you might be able to do something with Planck length on that scale. Basically, you'd have a ring that's transforming into different particles as you go around. But I've kind of shelved that idea now with the new research that I've been doing, which I could look.
I think the particle thing, when I look at it, I think the time is more correct. The Planck time is more correct than the length. So you have to multiply by the speed of light. So it will be CT, which is 10 to the power minus 26 or something. That will be more correct for the particle than, that's what I'm finding from discontinuum physics, than the Planck length. So Planck time is more correct.
Oh, interesting. Okay. Well, I mean, the Planck length is obviously to do with, you know, Heisenberg uncertainty principle, isn't it? And we're getting into quantum gravity at a certain point. Like you're reducing the radius of the uncertainty, saying that the particle lives in a certain place.
From a geometrical point of view in iSpace, it doesn't matter if you choose the length in Planck length, or the time in Planck time, or the mass in Planck mass, because they are all over simple relations related in Haber C over G to the exponent of your C. So you get C to the power of 5, you get Planck time, C to the power of 3, you get Planck length. And if you reverse the denominator and the divisor, you get the Planck mass. And these are well-known equations in quantum theory, but it is all dependent on the geometry of G. This is really that simple. And from iSpace theory, I have a G, and I can see that whatever you feed in from the Planck constant, and the Planck constant is so super simple in iSpace IQ unit system, it cannot be wrong. So we can debate over the relation to G in the sense of what I put in to get the proper SI value of G, but even that is debatable if it can be wrong. It is so simple that it should be correct, and that means that whatever you choose, time or length or mass, has no priority. It is exact because the C squared is the difference, and C squared is an integer value by definition of the SI. It doesn't really matter, neither from precision nor from logic or from physical preference. It's exactly the same.
Yeah, what are the reasons One of the reasons I say is that because the hot PDP circuit, I think, is critical to make the actual particle, because everything else will be like partons or quasi-particles. So at the 10 to the power minus 34, it may be quasi-particle or partons, but at the 10 to the power minus 26, it will be the actual particle, you know, like the electron or positron or things like that.
The question you have to answer yourself is, your theory needs a true continuum to work or not. If it is needing a true continuum, then iSpace is not related to your theory, in the sense that iSpace
it's become discontinuous
and there is no continuum. And
no continuum, because when the particle is forming, it separates. It becomes discontinuum automatically. The superluminal thing is continuum, probably. You know, there is no.
The problem is,
there's no time.
You have an energy. Is the energy a multiple of a minimum energy, or is it just?
It's a multiple. It will be a multiple. The energy
it will be a multiple. Then it is iSpace compatible automatically.
Yeah, it should be. So the thing is that the superluminal thing, there is no time in there. So in this subluminal thing, there is time. Like I said, the body creates the time, because only if the body is there, there is time. If the body is not there, there is no time. So automatically, when the time is there, it's discontinuum. You know, it's not continuum. So the superluminal thing, there is no time. So I don't know whether it makes sense to say continuum, you know, in that sense. It's like superluminal. That's it. There is no continuum, really. We
don't know the structure of space, and we don't know the structure of, surely not superluminal space. But I believe to know
there is no structure.
The structure of subspace, and that is
no structure. Yeah, there is no structure for superluminal. The subluminal, there is structure, and this geometry, which is discontinuum. There is no continuum. Like
what would be when the universe would be comprised of iSpace subcells, and these subcells would be drifting like a continuum?
Oh, that's where condensate important, because the condensate, what happens is the supercondensate, the superluminal becomes, when the hot PDP circuit, it becomes the particle. Then then evaporation back into the superluminal. So that's I don't know whether it's continuum or not, but that's a process that continues like a cycle. So from the superluminal becomes subluminal, then the condensate theory. So from the subluminal, it goes back into the superluminal by condensation evaporation process. So that's where that would be continuum. I don't know whether that's continuum or not. That's something we have to look at. I would think, because of baryon asymmetry, it may not be continuum. I'm not sure, but that's quite possible. Because otherwise, how do you create a constant speed? You know, how do you create a constant space? The space is still there. If it is continuum, that's reversible, then that space cannot be created. Same problem with the baryon asymmetry. How do you create the baryon asymmetry? You know, to create the real universe. You know, so that is the, you know, everything goes back to that to some extent. So that's something we have to resolve. I think the discontinuum aspect, if we look at it, the particles, they kind of separate. You know, it's like ice separating from water. You know, it's a phase. So
a phase change,
phase change. So it's like a multi-phase thing. That Emmanuel also thinks that way. He came up with the idea of multi-phase. We are going to work on it once Emmanuel comes back. That I think there are at least 3 phases. One of them is the superluminal, then the vacuum, which holds the speed of light constant, then the subluminal. So the vacuum is important to keep the speed of light constant.
That makes sense also, in my opinion, And by the way, I've read that, I didn't even know that the theory of relativity equations allow and endorse that. So they have a second set of solutions which are superluminal.
Oh, yeah.
Current papers books are not even mentioning that.
Yeah, that's the thing. Somebody squashed it. Somebody
drifted away and said that is like a relevant solution and cut it off, and then the next books took over only the cutoff types, and the original information is lost.
So Einstein cannot be blamed for that, actually. Einstein
this is all done post-Einsteinian,
Yeah. So Einstein probably thought, you know, although he mentioned that, he probably was falsifying himself, in the sense that they, only in that vacuum space, because he's talking about that speed of, the Michelson-Morley thing. That's only true in that in that phase of vacuum. But realistically, if you come to subluminar, so you have to account for. So, like I said before, I think the sound and light are interconnected. Just they transform to one to another. They are all the same thing. What you said about the positron electron, I was like 20 years ago, somebody from Intel talked to me, and because I was working before that, just before that, more than 20 years ago, and he asked, he was a scientist from Intel before I worked at Intel for a year, but not on science, but something else. But he asked me, so at that time, my idea very, very, I came from the experimental side, working with what you call the scanning tunneling microscope, things like that. I was an experimentalist mostly. So from that point of view, and I was thinking about the, in the scanning microscope, you have the tunneling aspect, things like that. So my idea, everything came from that. That was more crystal clear. And I agree with you. At that time, I said there are only positron electrons, vacuum, and they somehow combine together and they form all these things. So that was my simplest idea, come racer type of thing. So like even proton, that's why I want to check. The proton actually is in the force vacuum and it goes through vacuum decay. So that's why we have the weak radiation coming out from the nucleus when it becomes larger, like uranium or thorium, things like that. But so that's about force vacuum, where you can create mesons. And I'm writing a chapter now. I think in a week or two they are going to publish in that new book, that I think Gerd also may be having that IAP series. So we are editing that, and in that one I have proposed that the force vacuum you can form mesons, the true vacuum form fermions, and they connect through some wormhole, things like that, to create gravitons, things like that.
Well, wait a second. A meson. Well, remind me, what's a meson? Is it not two quarks, or am I thinking of something else?
Yeah, it is. It is the super. I mean, the strong particle. It's the strong force thing. It's a strong force particle.
Strong force particle is a gluon.
Yeah, but mesons come, by interaction. The mesons come. I have.
Is a family of particles.
Is two quarks bound by a gluon.
Yeah. Okay. So they are created by the quarks. I have to go back, but I remember that in the strong force, the quarks come and they join and they can become mesons. I have to look at how
two quarks make a meson, I think.
Yeah.
And but three would make a proton or a neutron.
Yeah.
But yeah, that is interesting. But when you talk about this vacuum, what did you say? Is that related to the vacuum
decay? Vacuum decay.
Is that related to the vacuum catastrophe?
No, it's actually, quantum field theory talks about vacuum decay. One of the results. I believe that will be correct. It talks about.
I just don't know too much about it. I heard you spoke about it last week.
Yeah.
I wasn't here, but I'm not too clear on it. I'll look into it though. It sounds interesting.
Yeah, and also Emmanuel also has done some video, and I watched that video of the person who talks about the vacuum decay, and it seems to be quite reasonable. He is explaining it quite nicely. Emmanuel sent to us like a few weeks ago. About
so it's not something that's going to destroy the universe or anything like
that. No. He talks about no. The proton is there. The proton is decaying, like in stars, and the idea of decay is that the proton then becomes isotopic, isotopes.
Yeah.
So you can create from proton, you can create deuterium, you can create a tritium, and that forms the star, the star system.
Yeah.
That produces all the energy of the universe.
The beta decay or whatever.
Yeah. So they have alpha, beta, all those things, gamma, all those things.
Yeah.
So
very good.
That makes sense. That all makes sense when you use the fact that you may be sitting in the force vacuum, and that's where, because force higher potential energy, force vacuum.
What does quantum or vacuum decay have to do with beta decay, for instance?
They are connected, but they are
in what way are they?
Different scale levels. They are the quantum level. The beta decay occurs at the quantum level, whereas the vacuum decay is somewhere, like I say, interface between the quantum and the astro phase. So yeah.
So that's where is there any? Wait a second. Is there any actual examples of this being detected?
You have to calculate that. I think this person, I think some quantum field theory, and but there is a problem, like you said, vacuum catastrophe. That may actually, the vacuum catastrophe may be a result of this thing. So that's what we are thinking about.
Right. Well, that's interesting. But what about the issue like that beta decay deals with, as you mentioned, protons and actual particles, usually intermediated by the weak force. But here you're talking about the vacuum, right? So what's in this vacuum? Is it just empty, or is it filled with virtual particles? Or
actually it is the strong force aspects. It is the strong force which are unstable, which are very unstable. So the Waltz vacuum itself is unstable, but it's a higher potential energy, and the true vacuum is lower potential energy. So because of the higher potential energy, it is very unstable. They will.
Now you are talking about the vacuum catastrophe, aren't you?
I think we can actually figure out. We have to do the calculation. I think that may show why there is vacuum catastrophe.
Why do you say the strong force is unstable? I mean, the strong force is, by the sound of its name, the strongest force there is. Well,
but you see, in the when the nucleus gets larger, it starts to become unstable, right? So that's the strongest, like uranium, things like that. The hydrogen is okay, but even hydrogen is actually, if you look at it, the stars, you have all these things combined together trying to form helium, right? The isotopes of protons, they form the helium. So they are not stable. They are not stable. But when
every element can have unstable derivatives of it, or to say that the period chemical system is not a line, is not a zigzag line, but it extends to a very much to above and below the line with its derivatives, which are unstable with lacking parts of electrons. And nobody yet has explained that series. We should not forget that is one of the biggest riddles of quantum theory. Quantum mechanics is all about the electron cloud of a proton. We don't even know what a proton is, but still have that nice theory of QED. And the QED theory is just a spin-off of the success of the QED theory. And while we think that QED is the proper description, at least mathematically, or we wouldn't have these computers and chips and everything like there, nobody has yet shown that QCD is just not a bad approximation yet.
Okay.
So this is why I don't believe in quarks. They have the same precision than G, and last week I showed you how easy it is to find an equation which is precise to 4 digits, and this is exactly what they're doing there. They have a one right result, and then they're guessing up, and if you are good in these things, you can make a model out of that which looks consistent. There is nothing wrong, as it is just a model. But if you believe it's real and you give all these novels about, yes, we have quarks detected and gluons detected, they have nothing like that detected, not in a single experiment.
Yeah, well, that's true. I mean, they do have their theory about, wasn't it they were like firing something at a proton and it scattered, and they got this idea of 3 elements inside the proton, and then
it looks like that two negative charged and 1 positive charged, two positive charged and 1 negative charged thing is inside that, and gave them the names of quarks. But if you would have the proper model, you could also say there are just 2 positrons and 1 electrons in a box, and we call that proton. And the dynamics of these 3 exactly mass-wise, electron mass-wise particles would be very, very different from gluons. Still, they have to give the same results they see in the accelerator. This is not a contradiction. It's just a completely different model. And more people thinking like that. It's not just iSpace theory going that path down.
I have heard the idea that this is what I was trying to get back to. Is it if you add a proton and an electron together, it gives you the same mass as a neutron? I think
it would not, because you need to explain the rest mass. And there is one paper from Nikolai Kozinov, which I already found 25 years ago from now, by the infants of the internet in that time.
Yeah,
literally. Yeah, I wasn't on Google search, because I think Google search wasn't even in place. It was Alta Vista or something where I found it.
Yeah, it wouldn't have existed in the infancy.
Yeah. But nevertheless, I found it, and today this guy is on ResearchGate. You can look him up, and he has a fractal theory of the atom. And I have calculated that with iSpace precision, and he was never fully to the point, but he is extremely close. That is really not a bad theory per se. It's just not giving the right values from today's necessary precision.
Well, yeah. But then you're saying that all these mesons then that Rajan was just talking about would have to be an electron and a positron together
in one way or another. Yes. Yeah.
Well, what do you mean in one way or another?
There's geometrically bound together in a way we don't understand. So look, when you put an electron 10 to the power of minus 12 meters, you're in the electron shells where you have just normal Bohr radius and everything is fine, and you do your chemistry. Now, there are ideas, but no proven theories that you can press the electron down to the core. And if you do that and lock the electron in, overwhelming the Coulomb force over there. You have to overwhelm the Coulomb force.
Yeah.
And when you do that, experimentally wise, it hasn't been done, but theoretically there are models, then they are getting stable inside the shell. Think your electron shell might be 6-dimensional iSpace wise with pi equals 3. There could be a pi equals 6 shell in a deeper area.
What I was asking at all. That was completely irrelevant. Like, it's a non sequitur. I was talking about mesons, which is 2 particles, not 3. But there's loads of different types of mesons, and they decay into different things, obviously. But
yeah, because they could have geometrically different. So think of the orbitals which electrons have. The orbitals make elements, chemical elements. Yeah.
Yeah.
When you take a same simple integer 1 over r squared plus 1 over, like the Rydberg constant, gives all your light emission possibilities, precise lines. Yeah.
Yeah.
And you could make a similar energy-wise thing in the core of the electron of the proton. Then you would get different masses for the same reasons.
Oh, well,
they are just in a box, a standing wave in a box with a nice geometry dance inside, and that would explain all the particles. So,
yeah, well, other reason is, the other reason is like Emmanuel is saying that electron is a Horn torus. So if we know that, if we know the geometry or the topology, can they go into each other and create that, create the protons?
So from iSpace, I'd say the electron is a 6-dimensional ring. Yeah. So a torus.
About proton,
I think that the Horn torus structure of Emmanuel is exactly that. When you visualize it in 3D geometry, you get the Horn torus. And if you visualize it in iSpace, you get some Lego fractal style structure. And a fractal style structure is per se not compatible to the field lines. But when you think of the field lines of 3-dimensional field lines, then a 6-dimensional element can have 3-dimensional field lines. That is not a contradiction, because the field lines will be outside and the 6-dimensional elements will be the quantum mechanical point particle inside. As I already stated last week, a Calabi-Yau has no outside per definition. Most people don't think about that, but it's that simple. When you fold the right side of something to the left side of a cube and the top side to the bottom side and the front side to the back side, you can do that in 3 dimensions for the first 2 operations, because when I bend the right of a Rubik's Cube to the left of a Rubik's Cube, I have a square-looking torus. When I then bend the upside of the torus to the downside of this torus, I have a real donut with a hole in the donut. And that hole in the donut has a pi Euclidean pi geometry, not a pi 3 geometry. It is a really normally looking donut. And then I have to bend the inside of the donut in the z direction to the outside of the donut. And I cannot do that in 3 dimensions. But when I do that, I start losing the visibility of that object because it's suddenly going away. It's a Calabi-Yau space. Everything left is bent to right, up is bent to down, and bottom is bent to front. Back is bent to front. And then makes in 3 dimensions, it makes it disappear. Or it's just a dot of not 0 size, but as small as you wish. The mass is still there, everything is still there, but geometrically it's gone. And this is why quantum mechanics, I believe, is right. And it looks like a point particle because it is a point particle when it is a Calabi-Yau space. And the inside of the Calabi-Yau space, only the inside living person in a 6-dimensional world could be, so a virtual flatlander or something could visualize that. But from the outside, you see nothing because it's warped.
Well, actually, that whole area that you're discussing there is, I would love to see a paper on that, like showing how similar is it to the Calabi-Yau spaces that they discuss in string theory.
This is easy. I don't need a paper for that. I mean, I'm saying the mathematics.
No, but just for like people to read with some images, and that that I could maybe I'd be able to. I just like a bit more.
The link which I gave you shows a fractal 6-dimensional subspace explained to derive all constants of nature which are there by deriving G first. The G derivation is the basis of all of that, interestingly.
How about positron? What structure positron? Is it inverse of the electron? What structure does it have? What topology or what geometry positron may have?
The positron has no different geometry than the electron. It's just a different charge. It's the opposite direction in this space. Nothing more, nothing less.
But it probably inside out because the charge. How do you get a positive charge? And so the charge
manifests in 10D. So if you have 60 subspaces, so a normal space-time projection, when you look at the images of other physicists like Hossenfelder or whatever, you look at one of her videos, then you see you have this three-dimensional grid, which is space-time, and on every grid intersection, you have a Calabi-Yau subspace. And that Calabi-Yau subspace, in my world, would be a rotating basis element of anything where potentially a quantum particle can sit. And when it wants to move, it needs to tunnel from one of such grid positions to the next grid position. And that's it about. And that is what it is doing.
So the rotation is different.
It needs to live in a box, and the box is the Calabi-Yau space, but it's sitting on the grid position, and that is what we call vacuum. So they have an infinite number of grid positions in vacuum, and these contain either additional energy in form of a standing wave of a particle or not. And when the particle moves, it transfers the energy to the neighbor cell by the rotational movement. That's why the energy transfer can only happen at speed of light, because all these cells rotate at the speed of light. And during one revolution, they can give all of their energy to the neighbor cell in the best case. And then you have a photon.
See, the disconium physics, we proved that actually there are 2 cycles. There is called charging cycle, and also there is a transmission cycle, or, so the charging cycle that creates the energy, whatever the quantum of energy, the charging cycle. And then in the transmission cycle, it transmits, or it creates the movement, the linear movement of that charge, which is what the photon is. So I think we proved that there. So that makes sense from that point of view. But also, I think for positron, it could be, I'm not sure, but in one of them, it could be flowing inside. For example, positron.
It's just a different flow direction. Yeah. So the Emanuel's charge has a tube inside, and when the tube is flowing inwards from the top, then you have an electron. The flow is reversed, and it is flowing to the upward, then you have a positron, and that's simple.
That's probably true. Yeah, that makes sense.
Oh, right. I thought, Rajan, you were saying that there wasn't enough like symmetries or something in this torus model.
I have to leave, unfortunately, right now for 2 different reasons. We're over 3 hours anyway.
Yes,
it was a pleasure talking to you. And if you have the time to look at the links, I would really appreciate that, because you're doing yourself not a favor if you don't look on my ResearchGate papers. One way or another, you will see that they are simple enough to influence your own theories. You will just have to trust me, my word for that. You don't waste your time reading that.
Okay.
Okay.
Thanks very much, Christian.
Yeah.
Christian, have a nice. Yeah.
Bye.
Yeah, we'll see you next week. We'll see you next week. Thanks.
Yes. So Rajan, you were asking about what was it? The structure of the positron and electron, yeah?
Yeah.
Matter and antimatter. I have something to say on that based on my new model thing.
Okay.
So here's like all of the stars. Well, this is about 53,000 galaxies in the SDSS catalog, and they're mapped to the unit sphere. And then we can rotate that 180 degrees and reproject it onto the tangent plane. Now, if we were to project this onto the, no, hang on a second. If we project this onto the tangent plane, we get what the universe looks like when we look into the sky, let's say. But if we rotate it, we get this. So this is like, you know, turning the universe inside out. Here's a three-dimensional version of it in here. That's the way the universe looks like. Earth is at the center there somewhere. And then when
that's on the tangent plane. That's on the tangent plane. That one. This one.
Right. Yeah, we're projecting from. Well, it wouldn't really matter if it is or not, because when you project from the 4D hypersphere into the 3D tangent space, it's just going to look like normal reality. Yeah. Oh. But when we rotate it, when we rotate the hypersphere, like I spoke earlier, we get this. So this is the universe inside out, and this is another angle of the same thing. So we see it's very spherical, and there's all the stars in the universe are contained in here, essentially. If we were to plot that, which we didn't do because that would be too many stars. But actually we can see if we plot like, what is it, 100 million stars? Let's see. We plot, no, just, sorry, 1 million galaxies, right? We can do that. Where is it gone? Here. So you see it drops off at about between radius 1 and 3 in this graph, and then it's quite sparse out the further out you go, and I predict that it continues to get more and more sparse, because when we turn this inside out, this prevents a singularity from happening in the center here, if you like. You know, it's not like really dense. Because it's falling off precipitously, it just manages itself. It never gets overly dense, never goes to infinity. So going back to this, yeah.
It looks like a hole in the second one, B, I think. It looks like a hole. Is that a hole?
Oh,
the black
sorry. Which B? This B or
no, another one. The three things you're showing earlier. I think it's on top. The three things, the projected thing. Yeah, that one, for example. Here it looks like
yeah, so it must be in this paper. This one.
Yeah.
Yeah.
It looks like a hole in the middle.
Up here.
Yeah.
Well, no, that's just the dense area of galaxies.
Okay.
So when we invert it, so this would be like putting if the Earth was the perimeter of the entire universe, this is what you would see. So first there's this dense wall of galaxies, then a more diffuse one, then another dense wall, and then just gets kind of.
That's where the black hole is, maybe. The black hole's maybe inside.
There's technically no black hole.
No black holes. Okay.
What I showed, well, not that there couldn't be black holes, but because of this distribution, because it's falling off as it goes out, it's getting, there's less and less. When you invert it and turn it inside out, if the distribution was the same here all the way out, and then you inverted it, you know, you'd have an infinitely dense point here at the center.
Yeah.
Because it's dropping off so dramatically, and it will continue to do that, I predict. Therefore, this is never going to get dense, because this will go to an infinite point here, but it will never go to an infinite density. In fact, the two will be exponentially related in some way. So if I go back here, so that's this is the same graph as the 3D one you saw, essentially. It's just the 2D version of that. And I think it looks like an eye. In fact, this whole thing looks like an eye, which is interesting because we have a point of projection here where the light is streaming in. So, you know.
Is it like a cone? It's like a cone that comes like that. Is it conical?
Oh, it's actually not a cone, no, because at the point of infinity, it's exactly right. So it's parallel. So there's light rays going, just striking across the top of this thing, if you like, you know. So it's interesting. Anyway, that's a good point. We can look into something like that. So there you can inscribe a 4D tesseract at the center of the universe. That's really more demonstrative than actual, but basically we're inscribing the 4D tesseract around the 4D hypersphere, and this that's important if you want to figure out the size of the 4D hypersphere. And we do that using redshifts and stuff. So I shouldn't say and stuff, but I was meant to show this. I'll have to, well, I don't think these values are totally correct anyway, because how to say this, when you project, I measured the values in the 3D tangent space, but those values are going to be different on the 4D hypersphere because I was measuring the projection and not the actual object. So I think you would have to convert the values a little bit, or measure it on the hypersphere instead of the tangent space. But so based on our perspective, the volume of the 4D hyperspace, which is the volume of the universe in 4D, is roughly now, these are like back of a napkin kind of, and they could even be wrong because I really did fly
back of the envelope.
Back of the envelope. Thank you. Yeah. So basically, roughly, I think the size of the universe in a 4-dimensional perspective is the golden mean to 10 to the power of 20 light years to the power of 4, which is, it answers the question, is the universe infinite or finite? We see it as both. Is infinite or non-orientatable from the point of view of the 3D tangent surface universe, but it is entirely finite from the perspective of the 3-sphere, because that is quite small, you know, when you think about it, compared to infinity. It's pretty small.
So
so
perspective. Okay.
Sorry, what?
Is it like a question of perspective?
What's a perspective?
Perspective means in the sense that how you look at it from the 3-sphere or the, you know, from the other one, how you use them.
Exactly. Well, if you're on the 2-dimensional tangent plane, let's say, the universe is going to look infinite. But if you're on this unit sphere, you know, it is finite, like. But it's not really a perspective thing, because even from the perspective of the tangent plane, this is still finite. And from the perspective of the unit sphere, the tangent plane is still infinite.
But when they calculate, they say it's a flat universe, right? I mean, it's closer.
Right, yeah, but we live on the tangent plane. So when we calculate it, we're calculating what we see on the tangent plane. So we're saying flat. We're also saying it's expanding. It's neither. It's curved. And the reason why we think it looks like it's expanding is because of the projection off of the curved sphere. In fact,
that makes sense. Like a horizon, if you see horizon, that's our direct vision. And I believe in that. That horizon is curved. You know, it's not flat. So,
well, yeah, I mean, if you think about it, so we're talking about a 4-dimensional thing. all like we're talking about perspective, like in terms of when we look into the distance, things get smaller. And on the unit sphere, they actually do get smaller as it goes up to the top. So what's up here is tiny, you know, out in the distance.
De-sitter versus de-sitter versus anti-de-sitter type of.
Yeah, kind of a bit like that. It gets smaller anyway as you go further up. So when you look out, I mean, obviously perspective from a biological sense is to do with how our eyes focus light and stuff. But if you remember that the entire universe is a bit like a giant eye anyway, then it makes sense that that's why our eyes work like that in a sense. It's kind of, it's top-down physics, you know.
And that's why
trickling
the
down.
The information theory I'm saying that 4 types of information with linear time and also non-linear time, that makes it 6. That probably might tell why, you know, that if you can use that, might tell why we see this difference. That
well, just to get back to that a little bit, just to finish my thought, so you'll have a clear idea. So basically, when we look into the distance and we see things are smaller, that is, it's hard to put this in a straightforward way, but that is equivalent to the scales that change on the 4D hypersphere. So when we see things getting smaller in the distance, in a sense, it's like looking into what's happening in the 4th dimension, where things are actually getting smaller the further away they are. So we could look at that and say, you know, those objects are actually smaller, if you like. But I don't want to push the boat out too far and make claims that are too ridiculous. But it's a way of looking at the universe.
So when we look at farther away, it's like 4D space. You're saying, is it like that?
Yes.
When you are closer, it's like 3D space. When you are doing closer, it's like 3D space.
Yeah, in a sense, but I mean, right. We're projecting from the unit sphere onto the tangent plane, and the tangent plane is located at -1 on the x-axis, on the z-axis. Sorry.
So we are on the tangent plane. So when we look at, that's why we feel it's infinite. But it's actually, you look further, you are going to 3D and then 4D. You know,
exactly.
Further and
but there is no distortion from the projection from the unit sphere directly downwards to the tangent plane at the z-axis equals -1. There's no distortion. But out here, there is distortion of relative sizes and appearances. And
that's interesting.
Right.
That may explain how we sense it, you know. I believe that there's space-time, but also sense. Like I said before, the sense is the, you know, ultimate thing that decides all the things. And in one of the papers, I have said that. So if we are looking at ourselves, maybe in the tangent plane we are looking, and then you are, you know, looking out further, you are looking 3D space, and you know that sense, and then further down 4D space. So that appears like a star may appear as a point, you know, from here, or twinkling point. So
well, that makes sense. Yes and no. I mean, basically, looking out along the tangent space in a way is equivalent to looking up through the 4D space.
Oh, it's like orthogonal. Are you looking at the orthogonal, or are we looking at the parallel to the tangent plane? You know, so if you are looking normal to the tangent plane, then you are looking at the 3D or 4D thing. But if you are looking at
the point I'm trying to make here is that if you were at the south pole of this sphere, you're located on the tangent plane. So you're in the tangent plane, but you're also on the sphere. So we are both.
Oh, it's intersection.
So we are at the intersection of the sphere and the tangent plane, which is, it kind of reminds me of what you're saying about being on the intersection of different. You know, you mentioned a couple of things there about vacuum decay and. I think you were talking about another intersection earlier, which I'm blanking on it at the moment. Anyway, so if I just wanted to get to this point, so it looks like if we say that things are getting smaller as they go out, yeah, there's an infinite amount of mass in the universe, obviously, as we venture out, but because it's an infinite space and there's always new material, but we see on the sphere it's getting smaller and smaller as it gets to the top. So it looks like there could be an equivalent. This could be wrong now, you know. I may have
wrapping around. It's kind of a wrapping around.
Well, yeah, but I may have I may have effed up something here in my thinking. But let's imagine I didn't, and I'm correct. But I think I might have. I'm just going to say it anyway, and we can disprove it later. So my thought is that there's an equivalent amount of matter outside of the inscribed tesseract. Where did it go? Or is this the wrong paper? Oh yeah. So outside of the inscribed tesseract, which is you see outside of this bubble here, this empty bubble, there's an equivalent amount of you know, I actually feel pretty stupid saying this, so I'm probably wrong. There's the same amount of matter out here as there is in here at the very center.
The density, the mass density changes.
I don't know what it is, but basically you can, right?
You multiply the mass density times the volume is the same as because the mass density at the center is more. So
yes, something like this. Yeah, yes, that is it. Right. So basically, what's outside on the sphere, when you have it like this, right, and then you rotate it up to here and project down. Yeah, you see, sometimes I get muddled up of what's going on, but basically, let's say you have this is the universe when it began, when it was starting off, yeah, and then you rotate the sphere so that it's now up here, or the other way around, I think, actually. Hang on a sec. Yeah, I think it is. Yeah, the other way around. So rotate it so it's at the bottom, and then you get this. And then if you rotate it again, you get that again. So the red point. So
is it one of them south pole, the other one north pole, or the?
Yeah. So this is north pole. So it would have to rotate. We actually have to rotate up, I think, in order for it to project. No, that's not right. Sorry, Rajan. I'm confusing myself. You know.
It's okay. You will come to it later. So that's next time.
Yeah, it seems like. Yeah. Anyway, I'm confusing myself. I'll have to think about it. If this is the way the universe looks, and then you rotate it. And then that's it. Anyway, there needs to be a scaling factor. So in order for all of these galaxies to fit inside this ring here, which is at the center of this, and to become that size, you need to scale it. And when you do the three-dimensional version, you have to scale it by a factor of 70, which is equivalent to the Hubble constant, which I think is interesting. Yeah. And also exponential growth factors, compound interest, population expansion. So that's pretty much where they get the Hubble constant anyway, I think so. But then there's other stuff as well. So we can figure out the exponential expansion of this space here, and then it becomes this, and then it goes back to this. So remember, the Earth is here. So as this expands, it's like I'm just taking a leaf out of Gerd's book that the line elements expands. There's more, what's the word? Degrees of freedom. So therefore more matter is created. So when we say there's you know, an equivalent. So then when it comes back to here, yeah, I don't know if it's correct to say.
It's not inflation theory, right? You are not.
No, it's not. Yeah, but the matter is kind of inflating. Like the size of the matter gets bigger as it goes out. There's more of it, in a sense. But you could have it. You could be right. It could be a density issue because okay. So let's say that was the theory anyway. That there's an equivalent amount of matter in the center, like ignoring that red dot in the center here as there is out here. So when we ask where is the asymmetry of matter and antimatter, well, there is no issue. It's like all of the antimatter is outside of the inscribed tesseract, and all of the matter is in the center. So this was my theory. It could be totally wrong. I mean, I might have been going off on one.
So I mean, that will solve the baryon asymmetry problem.
Yeah, this is the concept. So like if we look here, right, I've created a vector field showing this. Let's say this is positive matter with stuff radiating out from a central point. Then when we take the source and then the magnitude points and we convert them through the same method that I just showed, the stereographic method, and then we do the same with the source and grid, and then we multiply the and then we also take the backwards transform in a sense of that, and then we multiply the magnitudes by -1, then we arrive at this. So what I'm essentially saying is that when you take a positive electric field or whatever, yeah, positive charge field, and then invert it through the stereographic projection by rotating the hypersphere, you wind up with an inverted field. So this charge is now negative, which means it's antimatter. And then not only that, but it's also flipped. So like this arrow going out is now this arrow coming in here. So not only is it opposite, but it's also mirror image.
Symmetry. It's like mirror symmetry.
Yeah, it's actually, yeah, I think it's mirror symmetric, which means that this arrow going out is this arrow coming in, right? Not the top one, because that would be, the mirrors only flip left to right. Yeah. So, and the reason why it's only flipping left to right is because of this factor here, which is the multiplication of -1, because it's already, because the stereographic projection flips it across the x-axis.
So the arrow flips, the direction of the arrow flips?
When it moves out? Yeah, when you think about it, like if you look at the sphere again, this could be wrong. I'm just thinking about this.
Rotating. It could be a rotation thing, right? It may be rotating inside.
It is exactly a rotation thing. Like think about it. If there's arrows coming out of the south pole of this sphere in every direction along the tangent plane, so let's just select one. There's an arrow coming out here.
Yeah.
We use an exponential map or whatever, just project it back onto the unit sphere, and now the arrow is pointing up towards the zenith, yeah, as we might expect. But then when we rotate this by 180 degrees, what's going to happen to the arrow? It's going to be on the opposite side of the sphere over here, and it's going to be pointing down. So then when we project that back, it's pointing inwards, but from a mirror opposite direction. So that's really what isn't that correct? Wouldn't you say? Or
yeah, I mean, I thought it's more the North Pole is coming down and South Pole is coming up. Is that true? Is it rotating that way?
We're rotating it.
Yeah, it's going around
180 degrees, right? So if the arrow is coming out here,
yeah, it's going. Then it goes upside down. What is up is going to be down. Yeah.
Right. I mean, I could literally just draw it on an orange and then rotate the orange. We seem to be having trouble visualizing this, but right. Yeah, so yeah, it's going to be over here. It's going to be pointing down. So when we
that makes sense.
reproject it well, it's going to be flipping infinitely far out for a start. So that's a crazy point that I hadn't considered actually. That means right, if we go back here, that means that this arrow is not this arrow or this arrow. It is rather a point infinitely far away, isn't it? And it's the infinitely far away one of these, which is now this.
So correct? It's kind of involution versus.
It's like completely inverted. The field is totally inverted in at least 3 ways. You know, you've got, which actually is interesting because of the CPT thing, which is 3 things. It's so inverted. It's not only pointing out. It's, you know, it's in. If we have this as one dimension, it's pointing out. Here it's pointing in. Here it's on this axis. Here it's mirrored across. And the third one is, this is the closest arrow, and now it's the furthest away arrow. And this is the closest. So is there any other final thing to say? So that would appear to suggest that the whole thing is far simpler than what needs to be done here, because I project the information here, and then I have to use a backwards transform and multiply by -1 to get an image that looks correct. But
that may be same as positron and electron, like inflow versus outflow.
Oh well, actually, the reason why I may have to do that and why it's not working is because of a fundamental error I made. See this? Maybe this is the issue. Because I'm using a range between 1 and -1, whereas the actual field would be infinite. So
it will show us right side will be electron, the left side will be positron, something like that.
No. Essentially,
I'm saying matter.
This field is positive, so it's
that'll be positron. That'll be positron.
Yeah, okay, it's a positron.
And the other one
is negative, so this is an electron.
Electron. Okay.
But if you just take the most simplest one, I think you don't even need to multiply these by -1. But you see the way this has a kind of a flower structure, or like a cross shape. I think that's an artifact of the fact that this is a square. See? So when we project this onto the unit sphere and then invert it, then when we project it back, we get an inverted square, which is what this shape actually is. So
is it possible that actually you go, the one here, is it possible that the one that is going out is like electron, and then when it comes, the next one, when it goes inside, that's positron? Is it possible?
Well, you could just is a positron is a negative? Yeah, well, that would make sense, wouldn't it? Because a negative field is pushing things away, probably.
Yeah, that'd be electron.
Yeah. So, well, I don't think it doesn't really matter. Maybe one person's positron is another person's electron or something. So well, yeah, I mean,
electrons, the electrons from magnetic wave, so they kind of spread out. So that's what I'm thinking. Positron, they combine together and then eventually form like Christian also was saying that it can form proton. Like you, I think either you and Christian or both of you saying that it can, I also think that way, that they come together and, they accumulate accretion or accumulate together and they form a proton. And then I'm additionally saying that could happen in the false vacuum. That's the only thing we have to figure out. So that's why they become unstable and they form isotopes and all those kinds of things.
Well, yeah, that sounds really interesting. I'm not entirely sure. I suppose, I mean, I'm looking at this wondering, is this correct here? Because if we look at this, Now, if this field was infinite in extent,
okay,
like we'd imagine the electric field to be,
yeah.
So these arrows are going out infinitely. So there's no border here. So then when we reproject back, there will be this border, which is the flower, which is actually the border of the other graph, wouldn't exist. So these arrows would be going in. They'd be getting smaller and smaller as they go in. You can see that's a much denser, tighter field than this.
Oh yeah.
So that has me a bit worried, because it implies that the field strengths are just like way different.
No, they form. I think that's a difference in wave and matter, because when it is like this one, it forms a particle. It's like a particle. When the other one, it's like a wave. So that's where the quantum thing comes into picture about a particle, the duality. When it's compressed field, they form like particles. When it's expanded field, they form like wave.
Maybe, but I mean, why would this be a wave? Does that look like a wave?
That will be more like wave. The other one will be more like particle. That's my.
Oh yeah, I see what you mean. If these magnitudes are shifting, then it would be wave-like. Okay, Rajan, I got to go now, but
it was nice. Yeah,
and I think we've covered a lot of stuff. Your new research sounds very interesting. It sounds.
Oh, thank you.
It sounds complicated, but grounded in like solid ideas.
Yeah.
So I wish you luck with that. I think it's going to be really interesting. I hope just make sure that the stuff you're writing and putting out is really good quality.
And also your project, I am quite interested that how we are going to proceed. Like we initially said about the data, and you put the data modeling I showed you, and then you can convert into a function, and then you can use that to transform. And then
the transform stuff that you did, yeah. Did you? Yeah, I forgot about that. Well, I mean, I didn't forget about it, but I kind of moved ahead. I think I was telling you that basically what I was looking for from you was a space-time transform. But later, like I was busy with other things, and also I think you were busy with your own stuff. And then you said, I realized that I'm not dealing with the space-time manifold because there's no time as a dimension. So then I was thinking, well, there's no need for you to really attempt it, because by the sense of it, it would be an impossibility. But now actually thinking about it, I mean, surely, there's all sorts of tensors are used in all sorts of areas like electromagnetism and other places where time is not considered a dimension, right? So technically you could create a tensor, maybe, forward and backward transformation version of what I'm doing. But I mean, it would just be a different type of mathematics, wouldn't it? Like I'm using a very simple kind of form of maths, which is nice. And thanks for your help, by the way. That was interesting, combining all the equations to give to you to make the transform. But so shouldn't that have been enough to create the tensors? Because I never got anything from you.
Yeah, I mean, I think we need a lot. See, yours larger amount of data we need in order to really make any conclusive thing. Because the shorter,
like the way I have those sets of equations, and those sets of equations work on 10 points. They work on 5 points. They would also work on 10 million points. It doesn't matter how much data I have. The equations work no matter how much data I have.
Is it based on equation, or you get data from projections? You just project and then you get the data. And won't the data change? They don't become non-linear when you go higher levels?
I think you might be confused. Like, for instance, I use toy models, and then I use real data, yeah? So here's a toy model version, and that's what? 5 by 5, so it's 25 points. and then I invert that, and I get like this, you know. These are just examples. These are probably not right, but they're just give you the idea. That's a transform of the 10 points. Yeah.
But when you use the sphere, when you use the sphere and you get a concentrated point at the South Pole, for example, when you rotate it, you get a concentrated point on the North Pole, they become non-linear, right? The density changes, so that the equation will change accordingly.
No, the equation always stays the same. The results might be, like if I were to combine the two, let's focus here. Yes, these are better examples. The other ones were just different methods I was employing that might not be accurate. So here's your basic grid, and then you transform it, becomes the red grid, yeah? And then the blue grid is just this grid at the center here. It's just smaller because this is a bigger area. So when you add these two together, and then you want to look at, you're interested in what's going on here and what's going on out here separately, then that's a non-linear thing. I mean, this is probably non-linear as well. I mean, it's a Mobius transformation. So
yeah, the other one looks like a diffraction, you know. I mean, we look at the X-ray diffraction. I mean, I studied the electron diffraction. It looks like the one at the top, all the points, and the other one is like image. So when we have image of a crystal, right? They look like that, and then you do the diffraction, you get the other one, you know, the top one. So I think we need to.
Well, if you look at the bottom one with the red, you have a line.
Yeah, that becomes the image. That's like crystal or something. The other one is the.
Even say it looks a bit like a field graph as well. Look, this is like North Pole, South Pole, and then these field lines that come out are very they curve around, you know. So it's like a magnet.
Yeah. And
then you get the kind of field line in the center, but not really. I mean, it's a magnet of something. Anyway, it doesn't really matter. Yeah. But so basically what I'm saying is so that was using this equation, and the same equation can take this, which is 50,000 points, and turn it into that, or this. So it doesn't matter the amount of data. If you're able to convert what I gave you into some sort of not space-time metric, but just something like this, like an actual tensor, then fine. And if not, fine, because really doesn't really matter. But what I will say is your idea about a non-linear, what were you talking about? Some sort of SV, what is it called again? Support vector machine, SVM. Where you have the non-linear transform between the inside and the outside, and then we find the hyperplane division, I think they call it, the hyperplane intersection. That's really interesting, and I'm definitely going to employ that, and then I'm going to use that to generate other stuff later on, which will be could be very big in terms of well, maybe not. You know, the way you can say these things are going to be big and they're not that big. You know, they're like just a
You want to publish anything together? You want to publish anything together?
Well, yeah, absolutely. It seems like there's things are like some of your ideas that you've been having and some of the stuff I'm finding from this, there's a lot of overlap. But I would say if you want to publish stuff with me, it's got to be I would like it to be within this framework, you know? Like
I have to rethink about that. Let me rethink about it and see how it all fits together.
I mean, if you want, yes, absolutely. I mean, there could be like I'm going through this stuff now with you. You're like probably the first person I've gone through it with. So, and I'm looking at it going, oh, this is wrong. Maybe this is wrong. You know, maybe this could be changed. Have I got this right or have I got this wrong? But I think overall it's correct, and in fact, it's probably simpler than
it's quite interesting, and I think it kind of meshes the idea I had from material science about, you know, I was talking to a person that, you know, you had done very fundamental thing when I was doing my PhD, and you know, interesting thing we came out. What's the connection between a diffraction, you know, versus image? You know, the image is that of the crystal. You take the thing, and a diffraction, and what is the real transform between them? You know, that's interesting. So can you do inverse transform? Can we do
image? I understand. I understand the diffraction pattern of a crystal. What's the image?
Image is the crystal itself. You know, the crystal different sides. Like you look at the you know, the projection, the plane, or the side view, or the plan, or the, you know, elevation. So you look at the crystal from different sides. You know, essentially you are doing what I call projection. You know, stereographic projection of.
Would they be stereographic, or would it just be kind of more standard projections?
Yeah, standard projection, but stereographic, especially if you have a chirality or something for the crystal.
Great. Okay. Well, see, this is it. I mean, have a look at the model, because obviously it's fairly new, and you know, it'll take a bit of reading
time
to but there's, I think, you know, obviously you have your own work to do, and then you have your own research.
So now I'm trying to.
It might be a lot to take on, but I mean, if it really grabs you and you're like, oh yeah, I want to work in this, or maybe you're like, you know, so it's up to you really. But
a lot of time, what happens is I'm working on something which now I have to do, but eventually I may buy some time, you know, get some time, because I may be changing, and that may give some time. But when I move from the other one, the new idea strikes, and sometimes that, you know, that may be, you know, a refreshing change. Automatically I'm rethinking, and that gives a much more objective, more accurate picture of what it is. So this may be in my mind sitting there and it's working, and then doing something else, come back, suddenly something will pop out. Oh, that's, you know, it relates automatically. You know, the brain works that, I think. So I'm away from it, and then suddenly it pops out. Oh, there is a connection. You see the connection. And that, you know, that's what I like that kind of thing much better, because all the original things I have done is based on that. Suppose I keep thinking the same thing, or you don't get you know, a connection a lot of times. You know, you are making wrong connection sometimes. Even, you know, I felt that I was making wrong connection, but, you know, not always that helps. You know, but a lot of times you sit, you know, it sits there, and then later on it comes up and pops up, and then bingo, you get the, you know, the correct answer for that. You know, like Christian was saying, I think you were saying, I think that is a lot better, because you are, you know, you are looking at more objective aspects, you know, than getting, you know, biased by some, you know, your subjective thinking. You know, so like objective thinking versus subjective thinking, I think. So, you know, so I want to really see, you know, whether the objective thinking will, you know, give me enough things. I always believe in that. And like the information thing again, you know, I'll be thinking about that. I think that's a good idea about how the information travels.
Yeah, well, actually, if you think back on what I was saying with the it's not this paper. Hang on. Maybe this one. Yeah, the quantum gravity one has, I don't know if there's any images, but obviously you read this. But with the magnetic monopoles transmitting data from the source through the hypersphere onto the tangent plane, and that has to happen instantaneously. So that could be like an information transfer.
Yeah,
it's a torsion field. and that's how that's why
yeah, that could be. See, that's quite possible that information, that gravity information may be torsion field, whereas the photon information may be, non-torsional,
Well, this is true also of the graviton that you guys were discussing today, that seems to be traveling at the speed of light as well. So that's non-torsional. So there's a difference between the magnetic monopole torsion gravity wave, maybe, or whatever it is, and then the gravitons on the tangent plane. There's also work that another guy on or to the G did that I can see he had some interesting ideas. There could be the idea that a lot of quantum stuff is happening on the hypersphere, and a lot of the macro stuff is happening on the tangent plane. Oh. Do you know what I mean? So somehow there's like 4D aspects to quantum particles. Even so, we live in a 3-dimensional space, but it's being projected from a 4-dimensional space. So that explains the 4D aspects of the quantum particles. And it's being projected by light rays that are in a 4-dimensional space. So the light rays themselves are 4-dimensional in sense, and therefore they carry with them the information of this 4-dimensional hypersphere. So that may be why, we see things like spin 1/2, why SU3 can be converted into 4-dimensional rotations, which, whether you believe in quarks or not, doesn't really matter. It still have to be some sort of, if you're talking about a twisted, weird geometry of a positron or an electron, that could still be considered a new particle in some sense, you could still just call that twisting of that particle a quark, or, so we don't need to get too bogged down into those details, I don't think. But so it could have, and then there's other 4-dimensional aspects that I've looked into quite extensively, Clifford rotations for spin 1/2. I think I even found some 4-dimensional analogs for this Stern-Gerlach experiment, and different things like that. I mean, obviously there's huge areas of potential research here to do with quantum tunneling, quantum entanglement, even wormholes on the hypersphere, if you want to go that way. There's going to be a code where stuff. I'm thinking about how do you say funding, right? So funding proposals and stuff. But I'm a little bit busy at the moment. I'm also kind of funded already, so I'm a bit worried about getting too much funding. And that's kind of the way more money, more problems. That's saying. So I'm a bit worried about that. I'm gonna stop sharing.
Yeah. So one of the things interesting.
Imagine like let's say we get like, I don't know. This is theoretical, obviously, but might as well end the stream here. But